Good evening, everyone. I welcome you all to the day 5 of the Atal sponsored 6-day faculty development program on medical imaging in the third dimension, organized by the Department of Electronics and Communication Engineering, Maharaja Agarsen Institute of Technology. Over the past few days in this FDP, we have witnessed engaging discussions, insightful presentations, and a tremendous sharing of knowledge, and today we can expect more of the same. Today's session will be on testing of deep learning models in clinical applications by Dr. Nitin Arvind. He also took one of the session yesterday, so let me reintroduce him. Good evening, sir. Dr. Nitin Arvind Shalke is an assistant professor at the School of Computer Science, Engineering and Technology, Bennett University, Greater Noida. He has an extensive work experience in research, teaching, corporate training, and also has a consultant data scientist with multiple organizations in the past. He received his PhD degree in computer science and engineering from TIET Patiala. His research interest includes machine learning, deep learning, multimedia security, and NLP, with multiple publications in SCI journals and international conferences. He has one patent granted by the Australian government and has published two patents in Indian Patent Journal. We welcome you, sir. Over to you, sir.
Yeah, thank you so much, ma'am. Yeah. So, do we need to wait or we can
So you can start.
start with the session?
Right. You can start, sir. People are joining. 40 people are there. So, Nitin, sir.
Yes, sir. You can start. There is no problem, sir. Yes, Shalke, sir. Is there any problem to join? I think some connectivity problem is there. So please hold on for some minutes. Yes, sir. Will join soon.
Hello, I'm audible.
Yes, sir. You are audible.
Yes, sir.
Hello,
Yes, sir. Audible. Audible.
madam, I'm audible.
Yes, sir. You are audible.
Audio. Okay, let me check.
So please share
Hello,
your screen.
hello,
Yes, sir. Audible, sir.
hello.
Audible, sir. Audible.
Sir, you can share your screen. You are audible.
Hello.
Yes, sir,
Yes,
you
sir.
are very much audible. You can share your screen.
Your voice is. हाँ.
Yes, Nitin, sir. Can you hear my voice? Dr. Nitin Shalke. Hello. सर अब आपकी आवाज नहीं आ रही है इधर. Your voice is not coming, not audible.
Hello.
Yes, sir.
I'm audible.
Yeah, audible. Yes, sir. Your voice is audible. Yeah, good. Sir, I think some problem is from your side. If you change your network, I think it will be better.
Hello. I'm audible. Hello.
Yes, sir.
Hi,
Yes.
yes, sir, you are audible.
Some issue is there. Hello. Hello.
Hello, Nitin, sir, you are audible.
Hello. I'm audible.
Yes, sir, you are audible.
थोड्या वेळापहिले आवाज होता. Hello. Hello. I'm audible.
Hello, sir. Yes, sir, आप audible है.
Now you are audible. Okay. At my end, Okay, I'm not getting your voice. Okay, let me connect my headphone and
Okay, sir.
acknowledge me once again. I'm connecting the
Okay, sir.
headphone. Now, I'm audible.
Yes, sir, you're audible.
Okay, now it is perfect. Okay, let's start. Let me share my screen. I hope my screen is visible.
Yes, sir.
Okay, yeah. So good evening, all of you. Okay, so today we are going to discuss the advanced technique for the medical imaging. So uh, yesterday in the last session we started with the medical imaging. Okay, so under that we discussed the use of deep learning in the field of healthcare, and specifically the image related data. We discussed the key applications in the medical imaging. Under that, we discussed the several applications like disease diagnosis, okay, predicting the tumors, and the several applications we discussed under the medical imaging. And we discussed the generalized life cycle for implementing the any AIML model. Under that, we discussed it is started with the problem statement identification, then the data collection, then data pre-processing. Let me write here. In the last session, we started with the medical imaging and deep learning, and we discussed the use of the deep learning in the field of healthcare, where we want to perform the automation and we want to come up with the intelligent model, and that model can take the decision in the field of healthcare. Then we discuss the generalized life cycle for implementing any AIML model. For implementing any AIML model. Under that, we covered the cycle like problem statement identification, then data collection. Okay, so we identified a problem, that is brain tumor detection. Okay, and we did the implementation for the same using convolutional neural network. So based on that problem, we need to collect the data. Okay, so in our case, it was a brain tumor data set. Then the data pre-processing, where we want to convert the raw data to the meaningful data, knowledgeful data that model can understand. Then selection of the model phase, where we select the model based on our problem statement. Okay, if my basically in AIML the problem statement, it is based on your data also, and it is based on the types of problem that you have. If suppose it is a problem related to the text data, then we have the model like RNN, LSTM, BiLSTM. Okay, transfer learning model in the field of NLP like BERT, T5, GPT. Okay, if it is image related data and if it is a classification problem, then we have CNN, ANN, then transfer learning model like VGG 16, 19, ResNet, AlexNet, MobileNet. So based on our problem statement, we have to select the model. Okay, as far as our problem statement concerned, we selected the convolutional neural network in our last session. Then after that, after selecting the model, we need to train the model. So that phase is model training. We provide the training data set to the model, and we uh, mm, come up with the trained model. After that, we go for the model testing, where we evaluate the performance of the model. And if at the same time we evaluate the performance, and if the model is working fine, then finally we go for the real world deployment. Okay, the real world deployment. Okay, so this is the thing that we covered in the last session. We discussed the CNN model. We started with the deep learning fundamental in the last session. Then we covered the ANN, the basic ANN structure, what exactly it contains. Deep learning is implemented by artificial neural network, and in artificial neural network we have input layer, output layer, and set of hidden layers. And in every layer we have a node, and all these nodes are interconnected via some weight. Okay, and one more thing that we have discussed, that named as activation function. This activation function is used in every layer. Okay, and we discussed few of the activation function. We just discussed the thumb rule. We didn't discuss the internal mathematical aspect of this activation function. The popular activation function that we discussed, it is ReLU activation function, then sigmoid activation function, and softmax activation function. Under that, we discuss one thumb rule whenever we go for creating the deep learning model. Okay, and we have to add the layer, and in every layer we have to use the activation function. So if it is output layer, then we take the use of sigmoid and softmax based on the problem statement. If my problem statement belongs to the binary classification, then we take the use of sigmoid activation function. If my problem statement belongs to the multi-class classification, then you can take the use of softmax activation function. And in the rest of the layer, we take the use of ReLU activation function. In the rest of the layer, we use ReLU activation function. Okay. Then after that, we discuss the architecture of CNN. CNN architecture. Okay. So in CNN architecture, we discuss it is having input layer, output layer, and set of hidden layers. And in the set of hidden layers, it basically having a special kind of layer. That the first layer that it is having, it is convolutional layer. Okay. Then second one is max pooling layer. Third one is flatten layer, and third one is fully connected neural network, FCN layer. Okay, or you can say the dense layer. Okay, so this CNN basically having the input layer, okay, output layer, and in the middle it is having set of convolutional layer, max pooling layer, flatten layer, and fully connected neural network. All these layers are interconnected with each other. Okay, and these are the nodes in every layer. So this structure we have discussed and we implemented also. We have added the convolutional layer, we have added the max pooling layer, we have added the flatten layer, and we have added the dense layer. By adding these layers, one can extract the important feature from the images. Okay, so basically image contain lot many features. Okay, and we want to extract all these features, so we take the use of this convolutional layer. Convolution layer means your image is passing through the filters, multiple filters, and at the same time it basically reduces the dimension of the image when it passes through the convolution layer. Then max pooling layer is used to for the pre-processing of the image. It basically highlight the important feature and reduce the dimension of the image, or you can say the downsample the image. Then flatten layer flatten the matrix. Okay, so basically we have the output of the max pooling layer is the pooled feature map. Okay, and that pooled feature map is in 2 dimension, and using flattened layer it get converted to the 1D vector, and that is given as an input to the fully connected neural network. Okay, and finally the network is ready, and that network is basically used for the classification purpose. And we implemented one case study, brain tumor detection using this CNN model in the last session. Okay, now in the today's session we are going to discuss some advanced model. Okay, so in the today's session our focus is on this is our session. So our in our today's sessions we are going to discuss the popular deep learning architecture, and under that our focus is on transfer learning model like VGG16, VGG19, ResNet 50. Okay, we will discuss the architecture. Okay, we will discuss the importance of transfer learning, and we will discuss the hands-on associated with all these three models. Okay, VGG16, VGG19, and ResNet 50 on a brain tumor dataset. And at the end, we will discuss the future research direction in the field of medical imaging. Okay, so we will cover the theory. Okay, I'm going to cover the theory in 40 minutes, and rest of the time I'm dedicating to the implementation of this VGG16, VGG19, and ResNet 50. Even I want to show you one more implementation that is specifically for the artificial neural network. Okay, if I get the time I will show you that implementation also, but that implementation is on the Excel file data, not on the image data. Okay, so we will start with the popular deep learning architecture. We have artificial neural network, we have CNN, we have recurrent neural network, we have GAN, and we have UNet. Okay, these are the most popular network that we used in the field of medical data. Apart from that, there are several others. Okay, nowadays it is vision transformer VIT model. Okay, so that I have added in the recent trend. So ANN is basically, now you all are familiar with these terms, neural network, deep learning. Okay, so now we are directly going for the discussion. Okay, so artificial neural network is used for the task like disease predictions. Okay, in the healthcare domain, and where the data is in the form of Excel or CSV data set. Sometimes the data is maintained in the Excel or CSV file, like the data related to the heart disease, data related to the breast cancer, data related to the hepatitis. Okay, all these data is maintained in the Excel file, where we have input column, along with that we have output column. So input is associated with the output, that means a supervised learning problem it is. And in the target column we have basically a discrete data, as we are talking a disease prediction. Okay, so if it is cancer, there is a chance of cancer or no chance of cancer. So the data is in the form of discrete value, yes or no. Okay, so that time we have to use the artificial neural network. If the data is in the form of images, okay, and we want to perform the classification, or even we want to extract the feature, okay, then we take the use of convolutional neural network. It is also used for the task like segmentation and the disease classification. So CNN means it is not just the basic CNN, it will cover the transfer learning model also. Transfer learning model like VGG16, VGG19, ResNet, GoogleNet, MobileNet, AlexNet. Okay, so many transfer learning models are there that basically based on the convolutional neural network. Recurrent neural network is also used in the field of medical area, where when the data is sequential data, or you can say the time series data. So time series analysis of imaging data like ultrasound videos, okay, kind of signal, ECG signal it is, okay, then we can take the use of this RNN architecture. Then we have GAN. Under the GAN, the purpose of GAN is to create a data. Okay, so it is used for the data augmentation, generating the synthetic image for the training, and the image reconstructions, like enhancing the clarity of the medical scan. Then we have UNIT. Okay, there are several variation of UNIT also, UNIT plus plus. Okay, the modified UNIT. And this UNIT model is specifically designed for the segmentation. Okay, and when we talked about the healthcare, it is related to the biomedical image segmentation. It will combine the high resolution features with the spatial information. UNIT also somewhere down the line take the use of CNN. Okay, the base is CNN for the UNIT. Okay, out of that, I'm going to cover the CNN based the transfer learning model. Okay, so first you should know what is transfer learning model. Transfer learning is a machine learning technique where a model trained on one task is reused or fine-tuned for a related but different task. Okay, we can transfer the knowledge using this model. Basically, transfer learning means we can take the use of pre-trained model. Pre-trained model means that model is already trained on a huge amount of data set. Okay, and we directly take the use of that model knowledge for our problem statement. Okay, this approach leverages the knowledge gained from the first task to improve the performance and reduce the training time on the new task, especially when the new task has limited label data. Okay, that is challenging part. Okay, whenever we work on the real time project, challenge is we do not have the sufficient label data. Okay, whenever we work with the medical data, medical image data. Okay, so we don't have the huge amount of data. If I want to create a model, any deep learning model properly, then I need a lot much data. Okay, and getting those data, it is very hard. Okay, and here comes the need of transfer learning model. Key concept of transfer learning: a pre-trained model, as I told you, model that has already been trained on a large data set, usually for a task like image classification, language processing. These models have learned useful features or representations that can be applied to a new task. Then fine-tuning, the process of adjusting the pre-trained model for the new task. Okay, suppose I want to take the use of any pre-trained model for my problem. Okay, then you can fine-tune the pre-trained model. Okay, fine-tune the pre-trained model means what? You can remove the last layer and freeze the weight of that model, and at the end, okay, as a last layer you can add your layer. Your layer means whatever the problem that you have. Okay, according to that you can add that layer. Okay, we will discuss the implementation part also using the transfer learning model. Fine tuning involve modifying the model's weight slightly so that it can adapt to the new data. Then feature extraction, even you can remove the last layer and you can go for the feature extraction. Instead of modifying the model's weight, you can use the pre-trained model as a feature extractor. Okay, so these transfer learning model are used as a pre-trained model for classifying something, for predicting something, and at the same time it is used for extracting the feature also. That feature you can use for some other purpose. You take the output of certain layer, usually the last layer, and use them as a feature for a new training or creating the new classifier. Application of the transfer learning, it is in the field of computer vision as well as in the field of NLP. Okay, in computer vision we have the pre-trained model like VGG 16, 19, ResNet, Inception, MobileNet are often fine-tuned for a task such as object detection, face recognition, and medical image analysis. And in the field of NLP also, nowadays the concept of transfer learning is added, okay, from 2019. And model like BERT, GPT, and T5 are trained on the large text data set and can be fine-tuned for a task like sentiment analysis, text classification, and question answering. Our focus in this session is on the vision-based transfer learning model. So benefit is reduce the time, training time, okay, because we are using the pre-trained model, so that's why the training time is get reduced. Since the model has already been learned some useful features, the training time required for the new task is significantly reduced. Then improve the performance. Performance of the neural model is improved because of the use of this transfer learning. Transfer learning often provide a better result, especially when the new task has a limited data. Less data requirement. Okay, so that is the most important aspect. Okay, many a time we do not have the sufficient amount of data to train the model. Okay, and so transfer learning is especially useful in scenario where the data is collecting the data is expensive, as the model can make use of large scale data set from the similar task. Popular pre-trained model that we have, that is from VGG, that is Visual Geometry Group. They have provided VGG 16 and VGG 19. Then ResNet, Residual Network, Inception, MobileNet, EfficientNet, GoogleNet. Okay, there are so many pre-trained models. Out of that, we are going to discuss these models, VGG 16, 19, ResNet, in this today's session. VGG 16 is a CNN architecture developed by the Visual Geometry Group at the University of Oxford, and it is widely used deep learning model for image classification and transfer learning. So the base for this model is VGG 16, the CNN, Convolutional Neural Network. Architecture, so we have a series of convolutional layer and max pooling layer. Okay, so VGG 16 contain several convolutional layer, pooling layer, okay, several blocks of convolutional layer and pooling layer. So basically in the VGG 16 architecture, the input layer will take the image 224 cross 224 cross 3, that it will take the RGB image as input. Then the layers that we have, it is in the combination of convolution plus pooling. So the first one is 2 convolutional layer plus 1 pooling layer, okay, and with 64 filter. Then we have a block 2 convolutional layer plus 1 max pooling layer with 128 filter. Then we have 3 convolutional layer, 1 max pooling layer with 256 filter, and then 3 convolutional layer plus 1 max pooling layer, 512 filter. And finally, the fully connected layer. Fully connected layer means your artificial neural network, or you can say the dense layer, where we flatten the output, then 2 dense layer with 4096 neuron, each followed by the ReLU activation function, and final dense layer with softmax activation function for classification. Why it is softmax activation in the output layer? Because the data set that they have used, it is ImageNet data set that contain 1000 categories. Okay, so I think it should be there. So you can see in the first block the 2 convolutional layer and pooling layer. In the second block we have 2 convolutional layer, pooling layer. Then we have 3 convolutional layer and pooling layer, 3 convolutional layer, pooling layer, 3 convolutional layer and pooling layer. And this is your ANN, okay, fully connected neural network. Where in the dense layer, in these two dense layer, we use ReLU activation function. Okay, rectified linear unit that basically add the non-linearity in the input. And this final dense layer is having the activation function softmax. Okay, so this is the architecture of VGG16. So again, the detailed explanation is mentioned in the key features of the VGG16. The depth, the model consists of 16 layer. Okay, so as it contains the 16 layer, that's why it is called as VGG16. Okay, after VGG16, we are moving for the VGG19. So VGG19 means that model consists of 19 layer. Okay, so because of that, this naming convention is used over here. So among these 16 layer, there are 13 convolutional layer and 3 fully connected layer, 3 fully connected dense layer. Okay, convolutional layer uses small 3 cross 33 cross 3 filters with a stride of 1 and padding of same multiple layers, allows the network to complex the complex feature. Convolution layer we have already discussed in the last class, the last session. Pooling layer also we have already discussed. Okay, fully connected layer we have already discussed. The input image size requirement is 224 by 224 cross 3, and the pre-trained weight, often pre-trained on the ImageNet. Okay, that model has already been trained on the ImageNet data set that is having 1 million images. Okay, and the categories. Then how to use VGG16. So when we implement this VGG16, okay, at the time of implementation, we will use this code that we will uh, take the use of VGG16, okay, and we take the weight from the ImageNet, and we include top equal to false, and the shape is 224 cross 224 cross 3. Weight ImageNet means load the pre-trained weight from the ImageNet dataset. ImageNet is large dataset with 1 million labeled images with 1000 categories. Okay. The pre-trained weight helps in the transfer learning by leveraging the previously learned features. By and this parameter include top equal to false. It means it removes the fully connected layers at the top of the VGG16 model. Okay, so the last layer, by adding this include top equal to false, it will remove the fully connected dense layer at the top of VGG16 model, and this allows us to custom layers suitable for a brain tumor classification task. Okay, whatever we are going to discuss. Okay, at the time of implementation, I will explain this again. Then VGG19 is a CNN architecture that is widely used in vision task. Okay, it is exactly same as like that of VGG16. Only matter is the layers. Okay, few more layer are added, and because of that, we can say it is a very deep convolutional neural network. Okay, for large scale image recognition. So it was introduced by the VGG group, and it is described in the 2014 papers of very deep convolutional neural network for large scale image recognition. Why the word used very deep? Because the more number of layers are added, and layers are same as we discussed in the CNN architecture in the last session, that you can add as many as layer. Okay, but if you go if you add more layer, okay, in the normal CNN, okay, the computational time will it will get increased, okay, to train the model on our data. Okay, so but at the same time, when we add more layer, when we create a deeper network, it can extract the features very appropriately, and you get a good result. Okay, so in VGG19, the structure is this. Okay, there are 6 blocks. Okay, and in the 6 blocks there are multiple layers that has been added in the architecture of VGG19. So convolutional layers, specifically 16 layers divided into the 5 blocks. Okay, so 16 convolutional layers are there and 3 fully connected layers at the end. So 16 plus 3, it become 19. Okay, so there are total 19 layers in this network. That's why it is called as VGG19. And again, in the output, softmax activation function is used at the end of the in the final layer. Okay, and in the rest of the layer, they take the use of ReLU activation function. Every CNN layer is followed by the max pooling layer. Okay, so you can see every CNN is followed by the 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 max pooling layer. And again, the depth VGG16 contain 19 layers, 16 plus 3, small filter 3 cross 3, max pooling 2 cross 2, fully connected layer at the end. Okay, and trained on the pre-trained weight, that is ImageNet. Then next architecture is ResNet. In the ResNet, it is called as residual network. It is used in the deep learning architecture that was introduced by Kaming and his colleague in the paper, the Deep Residual Learning for the Image Recognition in 2015. It basically addressed the problem of vanishing gradient in very deep network, which can make trained deep neural network more challenging. The key innovation of ResNet is to use the residual connection, also called the skip connection, which allows the model to effectively train very deep architecture without degrading the performance. So vanishing gradient problem is a problem where the gradient become very small, almost zero. And when the gradient becomes zero, okay, it will create the problem to update the weight. Okay, updating the weight during the back propagation. Okay, so back propagate in the back propagation, this the gradient, okay, approaches to the zero, and because of that the problem occurs. Okay, and these kind of problems occurred in the sequential data. Okay, like in the text data. Okay, so this vanishing gradient problem is very common in uh, the RNN architecture. Okay, LSTM architecture, when we want to deal with the sequential data. Okay, if the sentence is too long, okay, and then the model is not capable enough to remember the words. Okay, and in the vision specifically, this problem occurred because of adding the more number of layers. So when the data is passed from one layer to the another layer, some data is get lost. Okay, and cannot get remembered. However, it is not required in the image it get remembered. Okay, but the challenge over here, it is the gradient. Okay, so gradient become very small, and because of that weight updation problem occurs, and we want to handle this problem. And to handle this problem, ResNet comes into the picture, and they added the residual connection. So this is the architecture of ResNet 50. Okay, so there are several framework of ResNet. Okay, ResNet 50, then ResNet 18, ResNet 34, ResNet 101, ResNet 152. Out of that, ResNet 50 is one popular framework that has been used by several researchers. 50 means there are 50 layers. Okay, you can imagine, from in VGG 16 we have 16 layers, in VGG 19 we have 19 layer. In yesterday's sessions, hardly we have added six to seven layers. Okay, so layers are increasing, and because of that, we are creating the very deep neural network. Okay, very deep neural network that can extract all possible feature from the image data. So ResNet 50 basically contained 50 layers. So it is more than VGG 16 and VGG 19. So lot many time it provide a good result when we go with the ResNet 50. Now, for a ResNet 50 architecture, the model consists of initial convolutional layer. Okay, as I told you, CNN is the base architecture. Whosoever want to enter into the field of this deep neural network, okay, and image processing, okay, they should know the CNN architecture very well. Okay, otherwise this transfer learning architecture is not having any use. Okay, you don't understand what does it means, the initial convolutional layer, the pooling layer, fully connected output layer. Those who understand these basic terminologies, they can only understand these architecture. So the model consists of initial convolution layer, then series of residual block. The purpose of this residual block is to transfer the information from one layer to another layer without loss, so that that vanishing gradient problem doesn't occur. Each block has convolutional layer 1 cross 1, 3 cross 3 along with the skip connection. Then global average pooling layer has been added over here, and then after that fully connected output layer in the case of classification task. In the ResNet, as I told you, there are different variants: ResNet 18, 34, 50, 101, 152. Higher the number of layer, the more complex the model, which typically leads to the better performance on the large data set. But at the same time, as I told you, when you create the deeper model, it will become computationally expensive. Okay, so that also we need to keep it in our mind. If you have the good system with good hardware, then we can think about the ResNet 152 also. Okay, but when we have the personal PC, personal laptop, then we take the use of ResNet 50 with 50 layer. Key feature of the ResNet. So some of the features we already discussed, like residual connection and residual block, the use of this residual connection and residual block. So basically in the plain CNN architecture, they add this kind of novelty, that they want to avoid the vanishing gradient problem, and by adding they know they that time the researcher are facing the problem when they add the more number of layers, the vanishing gradient problem was there. Okay, and they wanted to solve this problem. Because of that, they have added this residual connection and residual block. They introduced the skip residual connections that allows gradient to flow directly through the network, addressing the vanishing gradient and enabling the very deep network. The model is composed of residual block and residual block that add the input of a block to its output, enabling the efficient learning even in the deep network. Then deep architecture. ResNet allows the training of extremely deep network. Okay, like I have shown with 50 layer, with 101 layer, and even with 152 layer without degrading the performance. It will take the use of global average pooling. Instead of taking the use of fully connected layer, ResNet uses global average pooling, reducing the problem of overfitting and the number of parameters. Okay, then effective for imaging tasks. ResNet excel in the image classification, object detection, computer vision, leveraging its deep architecture and residual learning. Okay, so this is about the ResNet. Okay, now we will move for the implementation. Okay, so we completed with the theoretical aspect and conceptual aspect of the transfer learning model, like VGG 16, VGG 19, and the ResNet. Okay, all three architecture are based on the convolutional neural network. Okay, now we will move for the implementation. Okay, let me open the Jupyter notebook. Okay, the first model that we are going for implementing, it is VGG16. So to use these models, okay, we need some libraries. So we need to import the TensorFlow, and we have to import the Keras. Okay, then I'm going for creating the model. Okay, so I want to take the use of VGG16. Okay, this time I'm not going for the creating the base model, CNN model. I will take the use of pre-trained model for the brain tumor detection and using VGG16. Okay, so first from TensorFlow, we have to import keras dot import VGG16. Okay, this is the model that we need to import. And apart from that, you know, in the last session, we import the sequential model also. Sequential model means that is for fully connected neural network. Okay, and it is used, it is under keras.models. Sequential. Okay, we already discussed this sequential model. Okay, importance whenever we go for the scratch implementation, okay, of implementing the neural network, okay, we need this sequential, very important it is. Then we need a layers. Okay, so the layers are defined in the keras.layers. Okay, and from that we need different layers. So this time I'm not interested in the convolutional layer, max pooling layer, as we are taking the use of pre-trained model. We just need the dense layer that we used in the fully connected neural network and flattened layer. Okay, now execute. Then load the pre-trained model. How to load the pre-trained model? VGG16. Okay, and we are loading this model basically without the top, without the top layer. Why we are loading this VGG16 without the top layer? Can anyone answer? Why we are loading this?
We can add some custom defined layers.
Exactly, so that we can add some custom defined layers for our task. Okay, by default, this layer can categorize the 1000 categories. Okay, and you can provide any data. But I want to fine tune this model for my application. Okay, so that's why we are not including the top layer. Okay, we are going to use the weight. Okay, so I'm executing this first. Base model equal to VGG16, I need to add something. Okay, I don't want to take all these. Okay, I want to add the weight and this parameter that we discussed. That's why it is taking time. Let me show you. Okay, weight equal to ImageNet, include top equal to false, and this shape. Okay, this is what I want to add. This model is downloading. Let me copy this so that I can save the time. Okay, so by adding this include top equal to false, we are not loading the final layer. Okay, model with final layer. Okay, so downloaded complete model completed. Weight ImageNet include top equal to false and input shape is 224, 224, 3. Okay, and executing this again. Successfully executed. Okay, we have taken the use of this ImageNet. Okay, and we have used these weights. This model is trained on the 1 million labeled images. Now, next we will move for the freeze the base model. Freeze the base model layer. What do you mean by freeze the base model layer? Can anyone tell me what do you mean by freeze the base model layer? I'm going to use one loop for I in the base model dot layers and this I means your layer. Okay, the trainable equal to false. Execute. Okay, with this we freeze the base model layers. So freezing the base model layer means what? We are fixing the weight. Okay, now the weight is not get updated. So it is a technique to preserve the knowledge that the pre-trained model has learned. Okay, so I hope it is clear. Okay, because of that the layer will only pass the information. Okay, forward the input and uh, passing it to the next layer. Okay, I hope it is clear. So we basically
Sir, excuse me, sir. Can you explain again that freeze the base model layer?
okay, so basically by freezing the base model layers, weight of these layers will not get updated. Okay,
Okay,
weight
sir.
of the base weight of these layers will not be updated. Okay, that is the meaning of freeze the base model layer. Okay, we have already executed this. Now I'm adding the custom layer. Add a custom layer as per my requirement. Custom layer for the brain tumor detection or classification. So now we remove the last layer. Okay, as per the architecture, this is the architecture of VGG16. So what we did here, we removed the last layer, this last layer. Okay, because we don't want to use their last layer, and now we are adding our custom layer. Okay, as per our requirement. Okay, someone can use this dense layer. Okay, for feature extraction also. Okay, means if they want to extract all the features and want to do something different, okay, want to add some kind of novelty in their research work, they can remove this dense layer, the final dense layer. They can take the use of this extracted feature and can provide these features to any other mechanism. Okay, even I have published my one paper, okay, that is related to the forgery detection with this VGG16, okay, not with the plain VGG16. There we have created some novel framework also, okay. So at that time, what I did, we removed this final layer, okay, and we extracted the features, and these features we have provided to the one novel algorithm for detecting the forgery, okay. So you can also use these transfer learning model in your research work, okay. Yeah. Now where we are, so add a custom layer. So I'm adding the custom layer. So custom, by adding the custom layer, we are creating our model. So I'm creating my model, I'm giving the name as model, and sequential, okay. You know the sequential, with the use of sequential we can create the neural network, okay. And in the neural network you can add the layer, whatever the layer that you want to add. So I'm adding few layer in that. So the first layer, that is in the sequential means dummy network. With the sequential, I told you in the last class, sequential means one dummy network, okay, dummy neural network. In the neural network we need to add the layers, first layer, then second layer, then third layer, and output layer, okay. So we add these layers, or if it is normal ANN, then we add first dense layer, second dense layer, third dense layer. If it is convolutional neural network, then it is convolution layer, max pooling layer, convolution layer, max pooling layer, and finally the dense layer, okay. Then we connect all these layers with each other like this. Sequential create the hollow network, okay. Now in this case, in the sequential, what we are adding, in the sequential we are adding the base model. This is our base model, okay. So complete base model is get added VGG16, but without output layer, okay. So this is the first layer, that is base model. Then I'm adding the flatten layer so that the you can flatten out the information. If the data is in the form of matrix, that get flattened into the 1D vector. Dense layer, okay. So this is my dense layer, okay. And in the dense layer you can add the neurons and the activation function. So activation equal to ReLU. This is basic thumb rule, okay. If other layers are using, then we take the use of ReLU activation function. And finally the output layer. In the output layer I'm adding the two neuron, and the activation function I'm changing here from ReLU to sigmoid. Why sigmoid? Can anyone answer?
So since it is having only two layers, it means sigma means binary output, sir. Yes or no?
Not layer. In our brain tumor data set, we have two categories only.
Yes.
Either tumor is
Both
there
are
or
there.
no tumor is there.
No tumor.
Binary classification. If there are multiple categories, then we take the use of softmax activation function, okay. Now the square bracket completed, and we have added this custom layer and execute, okay. Successfully we have added. What will be the next step? Those who have attended the last session, they know it. After adding the layers, we discuss with the sequential we create the hollow network, okay. With the sequential we create the hollow network, then we add the layers, okay. Then we add the layers,
Compile.
yeah.
Compile
After
them.
that, after adding the layer, we need to compile the network. Compile the network means, okay, create the connections, assign the weight, Okay, weight is get assigned whenever the one node is connected to the other node. Okay, so we take the use of optimizer, we add the loss, and we add the matrix. Okay, so I'm compiling the network. Compile the network. So compile, we have method model dot compile, and in the compile, whenever we we compile any neural network, three common parameters are there, okay, that we used on regular basis, whether it is RNN model, whether it is LSTM, whether it is bi-LSTM, whether it is GRU. Okay, any model that belongs to the neural network, we use optimizers. Optimizer equal to most popular optimizer Adam, then comma, loss equal to, it is binary cross entropy. If it is multi-class classification, then we use categorical cross entropy. If there are more number, then we have one more variation of this categorical cross entropy, binary cross entropy, matrix equal to accuracy. Matrix equal to accuracy. Okay. Let's execute.
Question.
Successfully executed. Okay, we successfully compiled our network. If suppose someone want to see the network, display the network.
Hello, sir. May I ask some question?
Yeah, tell me.
Sir, this Adam optimizer is always used in the dense ResNet, dense CNN.
No, you have the flexibility to play with the optimizers. Okay, we have several other optimizers.
Suppose
Right?
we use another optimizer like Pelican optimizer, whatever. So that case, we can replace this Adam by this optimizer.
Yes, you can. You can use RMS prop. Okay.
Label also. Okay,
Yeah,
okay.
RMS prop.
Okay.
RMS prop. Okay, there are so many optimizers. Okay, out of that, Adam gives us the good results. But again, when we go for the research, okay, we put this optimizers as a part of hyperparameter tuning. We collect the result across all the optimizers, and then we finally quote that with this optimizers we are getting the good results. Okay.
We
Are you
use
getting it?
at what place we have to use this optimizer after running this. Actually, I use Pelican optimizer, but whenever we use this optimizer, we get a much better result. But when we have to use this optimizer?
I'm not getting your questions. Okay, what exactly you want? Do you know the importance of optimizer? Why we use this? Why
Haji.
this is required? Tell me the purpose.
Because to get less the difference between the predicted value and the ground truth value. This
So
is
how
the
it is? How internally it is get like you are saying that whatever we are predicting, for example, neural network is predicting 100, actually it is 80. Okay,
80.
actually it is. That means there is an error of 20, right?
Yes.
Okay, then how it solve this optimizer?
Sir, every
Basically this error is get back propagated, okay, using back propagation algorithm.
okay.
And weight is one important parameter. Okay, the weight is very important terminology in the neural network. Only because of that weight, okay, we are achieving these things, the final results. And that the weight is get updated. Okay, that weight is get updated.
Okay.
in whenever this traveled, okay, like I want to reduce this 20, okay, this error is get back propagated, and the derivative will, the gradient, okay, will takes place with respect to the weight, and the weight is get updated.
Okay,
Okay,
okay. Mm-hmm.
getting
Thank
it?
you. Mm-hmm. Yes, sir. Thank you, sir.
So we have a list of optimizers, like RMS prop is there. Can anyone tell me another optimizers? SGD, stochastic
Ada
gradient
grad, sir.
descent, ADA,
Ada
ADA
grad.
delta, ADA delta, right? Gradient
There are
descent,
few
batch
there are few
gradient
latest
descent, okay? SGD with momentum, okay? There are so many optimizer, but popular optimizers are RMS prop, ADA delta, ADAM, okay? Again, this optimizers itself, it is a kind of one complete session, okay, for 2 to 3 hours. It is having so many things, okay, under the mathematics, how the things get updated. Back propagation algorithm is one important concept under the deep neural network, okay. So whosoever want to enter into this field, okay, my suggestion to go with this mathematical concept also, okay. So you can refer some book like uh, Yagnarayana and Zurada, okay. Although nowadays we are not going to use the book, okay, but those who want to go in the depth of this, how exactly these weightages get updated, the learning rate is calculated, the parameter calculation is calculated, so internally so many mathematics involved, okay. Yeah, I hope it is clear. Model, I want to display the network, so we have model dot summary, and you get the summary, okay. So in the summary we get these things, the first layer VGG16, flatten layer, dense final dense layer, okay, and with total number of parameters. These parameters are also calculated, okay, with the help of this updated weight and the bias calculations internally, okay. So this is your model summary, right? We successfully create the model, okay. We have created the model. Now see, this is your transfer learning model. In a simplified manner we have created this model. I hope it is clear. Any doubt over here at the time of model creation?
No, sir. No, sir.
Okay, now let's proceed for preparing the data set. Okay, we are going to prepare the data set, and we'll do the pre-processing, okay. And we need a data generator. Okay, I didn't import over here. Let me import first. Copy this. From tensorflow.keras, and in the pre-processing.image we can import a image data generator. Then we create the object and we pass the information for the data augmentation, okay. So we can use the rescale operations, decimal scaling you can use 1.0255, rotate the image, you can specify the rotation range, zoom range, then width, height, shift range, Okay, and we saved it into the train data gen. Okay, in our last session also we have prepared the data in the same manner. Okay, to do the data augmentation. Let's see. Okay, successfully executed. Then we use this train data gen dot flow from directory, and we pass the path. So path of our data set is users and brain tumor. Okay, I'm passing the path to load the data set, comma. I'm specifying the target size. Target size is 224, 224. Then, comma, batch size. Equal to 32. Okay. And you can save this data train gen. Okay, this is my training data. And execute. Okay, so we have loaded this 253 images that are belong to the two classes. I have taken a small data set. In the last session also I told you, in order to demonstrate these kind of model, okay, we need a sample data set. Otherwise it will take the time to train the model. In our data set we have two classes. Yes, the brain tumor is there, these images, and no brain tumor. Okay, now we have loaded the data set. What will be the next task? We have created the model. You can see that diagram. Okay, whatever we discussed in the last class. See, we define the network, we compile the network. Okay, and we have taken the data set. Now we are moving for the fit the network. Fit the network means the training. Training means whatever the model that we have designed, we are providing the data to this model. So to train the model, we use this method. Now train the VGG16 model. Okay, on our data set. So my data set is here, train gen. I'm specifying the epoch. What do you mean by epoch?
Iterations.
Iterations. Okay, so as in this case study, okay, the target size, the size of image that we are keeping, it is 224 cross 224. Okay, so it will take time if I will put the 10 epoches, okay, 20 epoches, 100 epoches. In order to save the time, I am putting only one epoch. Okay, epoch as 1. And you know, in whenever we worked on the project, we cannot keep the epoch 1. Okay, we want to keep this epoch maximum so that your model train properly. Okay, so it is exactly same that we read some concept 1 time, 2 time, 3 time, 4 time. Okay, so when we read some concept multiple times, you can understand that concept properly. In the same manner, model can understand the data. Okay, due to the time constraint, I'm keeping this epoch as 1. Let's see. Okay, Even with one epoch also, it will take some time. Now you can imagine if I am going to put 20, 50 or 100 epoch. Although this model will not give us the good accuracy. Okay. Why? Because we are just taking the one epoch. But if you increase the epoch, if you increase the size of our data set, if you play with the hyperparameter, you can get the good accuracy. Okay, so my one epoch is completed and I'm getting 53% accuracy. The reason behind this accuracy is that the epoch that we are using. If you pass the epoch, okay, like 50, you use the epoch, definitely you get the good accuracy around 85%.
Sir, I'm
Okay.
having a small doubt, sir.
Yeah, please.
Sir, sir, actually this output, so accuracy is 53.33, loss is 2.3919. If the loss is 2.3919 means it is either high or low, sir. That I am not able to understand, sir.
No, it is high. Loss is more here. But
Okay.
normally it is very hard to conclude something from the loss. Okay, so it is always better to see the accuracy. Okay,
if it is a negative loss means,
it is exactly similar. Like in the regression model, when we go with the regression model and we check the performance of the regression model, we have parameter like mean square error, root mean square error, median absolute error, and R2 score. Okay, so error should be minimum and R2 score should be maximum. Okay, that is the main agenda, right? So
sometimes the loss will be negative
error should be less and R2 score should be more. So to which you can target, whether you are going to target the error or you are going to target the R2 score.
Okay.
No, I am
Thank you,
asking
sir.
the question to you. I am asking this question to you. In the regression model, if I want to evaluate the performance, we have 4 performance matrix. That 4 performance matrix is get divided into the 2 part. Okay, like if it is regression, okay, like MSE, MAE, and RMSE. Okay, these are errors, and one is R2 score. Objective is, when can we say that my regression model is performing well? The model which is having the less error, less mean square error, less ME, and less RMSE, and good R2 score. Now tell me, on which parameter, on which performance matrix you will focus, whether you focus on this or you focus on this, to understand properly.
R2 score, sir.
R2 score, because it is hard. Okay, we don't know what should be the minimum, but you know the maximum. 100% mean maximum, right? So if we get the 0.8, that means 80%. Okay, but here in mean square error, it is difficult. 0.126, you get a result like this. Okay, so it is always better to take one as a reference parameter and another one as the secondary reference parameter.
Okay.
Yeah, done. Then train the VGG16 model. Training is done. Now you can move for the prediction. Okay, you can take the image, okay, and you can go for the prediction. Now, however, this model might be possible that you get the wrong output also. Why? Because model accuracy is 50%. We didn't train it very properly. We used very few images and we trained with a single epoch. Okay, so it might possible that it will give you the wrong output also for some images. Okay. Done. So I think the prediction, whatever the code that we have written yesterday for the, you can use the same code for the prediction over here. Okay.
तुमने करवाना है, मैंने करवाऊंगा,
So,
तुम करवा लेना ये काम।
yeah, someone is
आपने
talking, please.
बैंकों का करवाना है, आज बता दो।
Please.
राघव भी पूछ रहा था
कर लो
कि भी इसका लग नहीं रहा।
तुम कर सकते, तुम कर।
तुम्हारा ना एटीट्यूड
Please
बड़ा अजीब सा ही है।
mute yourself.
कर लो, क्या मतलब होता है? समझ में?
Okay. So after training the model, you can go for the prediction. Prediction means you can take the input image and can predict. Okay. So already this code we have written. Okay. In the last session. Okay. Let me open it. Okay. But it is not going. It is not guarantee us that it will work properly, because right now it is giving 50% accuracy. Okay, I'm just copying it, the same one. This is CNN model implementation, okay, that we did yesterday session. Okay, I'm just copying it. Okay, this is for the prediction. It is deep CNN model. In our case, it is only model. Okay, model.predict. Size should be different. Okay, target size in our last session it is 64 by 64, but today it is 224 cross 224. Even in the error also it has been mentioned. You can see. Let's check. Next error is the truth value of array more than one element is ambiguous. Okay, let me check. Yeah, so you can execute this prediction in CNN. You get the prediction. Okay, we use only one node. You can see in the CNN I have added in the dense layer I have added only one node. Okay, so that's why you get only one output. Okay, but here it is in the predictions I'm getting the two probability. Okay, two. Okay, so that means you have to use 0, 0. Okay, 0, 0 means this first one, 0, 0. Okay, that means this, and 0, 1. 0, 1 means this. Okay, so two possibility, tumor possibility, no tumor possibility, and execute. PLT is not defined means import matplotlib dot pyplot as PLT. Okay, now go for the execution. Okay, no tumor, you can see. Okay, why I have used here 0, 0? Because the prediction that it is giving, okay, prediction means the probability, it is probability. Okay, as we have used the two node, okay, here in the output layer I have used the two node. That's why your answer is not a single answer. Okay, it contains the array, and that array contains the two probability. Okay, because of that we have added this. Okay, I hope it is clear, right? So you can take the input and then you can check whether the it is tumor image or not. Okay, yeah. Now let me go for next model. If you understand this model, then it is very easy for you to understand the next model. Okay, our next model is VGG19. Sharma sir, hello. Is the organizer
Hanji,
is
sir.
there?
Yes, sir.
Yeah. So can I take 10 more minutes to take the implementation of this VGG19 and ResNet? Is this okay, or what exactly it is?
Yes, sir, you can take 10 minutes.
Is this okay, na? Yeah.
Yes, sir.
Interrupt me, okay, whenever the time.
Yes, sir. No problem. No problem. You can.
Yeah, okay, sir. Okay.
Okay, now the main challenge is to explain the first model. Now it is easy. Okay, now I'm going to use the copy and paste kind of thing. Okay, almost same thing. So only matter is to load the model. So now this time I'm going for VGG19. No need to copy anything. Okay, I'm going to use VGG19. So first I need to import the VGG19. Okay, VGG19. Okay, this should be object of VGG19. Okay, and rest will be same. Okay, rest will be same. So I'm adding all the things in the one single cell. Freeze the base layer. Okay, freeze the base layer. Then next, after that, add a custom layer. Add a custom layer. Okay, it is always better to clear the session. Okay, whenever we used create the model. Okay, it is always better to clear the original session. Okay, so I'm going to clear the session, the previously created session, using keras dot backend. It is, I think, clear. Let me check. Clear, no, clear session. Yeah, execute. No, it is function. Okay, execute. Done. Okay, we clear the session as we want to move for the VGG19. Now I'm going for VGG19 this time. Okay, and add a custom layer. Then we go for the compilation. I'm just copying the code from the top. Okay, exactly same, only one change is required. Okay, you have to import VGG19, you have to create the VGG19 object, and you have to no need to change anything. Okay, then compilation, and finally display the network. Okay, finally display the network. Okay, let's check, is there any occurrence of VGG16? No occurrence is there. Let's move. Now successfully we have created VGG19 model. Okay, we have successfully created the VGG19 model. It is exactly same to train the model. Okay, so the process is same. You have to prepare the data set, perform the data augmentation, load the data, and train the model. Okay, and go for the prediction. Okay, so I hope you understand the VGG19 model creation, right? So I'm not going for the model training over here, but it is exactly same as like that of VGG16, right? Now let's move for the ResNet. Okay, let's move for the ResNet model. Now this time again I'm going to create, okay, this is ResNet model for the brain tumor detection. I'm going to clear the session first. Whatever the existing session is there, it might create the problem. Okay, so it might throw the error. Okay, so it is better to clear the session and load the, copy this. Okay, I'm copying this thing. Okay, exactly same. This time I want to create the ResNet. Okay, so it is, we have the hand over here, and I want to go with the ResNet 50. Okay, so it is ResNet 50. ResNet 50 means we have 50 layers. Okay, and this is ResNet 50. Okay, even it is VGG19. Okay, this is VGG19. Now ResNet 50, object of ResNet 50. Okay, object of ResNet 50 and rest all is same. The freezing the base layer, add a custom layer, then compile the network and display the model summary. Okay, let's see, is there any occurrence of the VGG 16 or 19? No occurrence. Execute. Yeah, successfully we have created the ResNet model for brain tumor detection. Next part is get the data set, do the data pre-processing and data augmentation, and train the model using .fit method, and then go for the prediction. Okay, I hope all these three transfer learning model clear to everyone, okay, which we have used for the medical imaging. In our last sessions we discussed the basic model, okay, basic deep learning model, convolutional neural network, and in the today's sessions we discussed the advanced deep learning model, that VGG 16, VGG 19, and ResNet. Okay, I hope the hands-on part is clear. Now the last thing, and I'm going to wind up the session. Future direction in the area of medical imaging. So future direction, the federated learning concept is there, where training model across the decentralized data set without sharing the sensitive data set. Okay, so many a time healthcare data, some privacy that we have to maintain, and for that you can explore the area of federated learning. Multimodal learning is nowadays playing an important role in this area. Multimodal learning means what? Multimodal learning means taking the data, okay, in all possible manner, not only from image but also from the text, but also from the video, audio, clinical notes, to train the model. Okay, so that model can perform in a better manner and can handle lot many things. Edge computing, deploy the model on edge devices for the real-time diagnosis in the remote area. Personalized medicine, tailoring the treatment based on the deep learning and getting the insight from the medical images. Apart from that, there are several other future directions. Okay, one can take the use of vision transformer, Gen AI, okay, LLM in the field of healthcare. Okay, because this AI domain is become very strong. Broad domain is AI. Under that we have machine learning. Under that we have deep learning, and under that we have Gen AI. Okay, so one can take the use of this Gen AI in the field of medical imaging, and based on the data, several other fields get interconnected with this AI. If the data is text data, then NLP comes into the picture. If data is image, video, then computer vision and image processing field comes into the picture. Okay, so I hope all went well, and thank you so much.
Thank you, sir. Thank you so much. Any queries from participants?
Hello.
Yes, ma'am. You are audible.
Sir, I want to understand overfitting and underfitting in the context of deep learning. Is it
Yeah.
possible to explain this with examples?
Yes, it is very easy. Okay, let me show you. Underfitting and overfitting. Now, underfitting means what? Your model is unable to extract the important features from the image data. Okay, and because of that, it is not going to predict the result. Okay, that is the meaning of underfitting. In underfitting, you will not get the good accuracy on the training data set as well as on the testing data set. Okay, then overfitting means what? Overfitting means model is trained on the limited data. Because of that, your model is getting good accuracy on the training data set. Okay, you have the limited sample of images. Okay, and you are training the big model. So on that model, when you are training it, you are getting the good accuracy. But when you go for the testing the model, that time it will get failed. Okay, that time it will get failed and you will not get the good accuracy. That is called as overfitting. Okay, so underfitting is anyhow we do not require. Okay, there we have the problem like bias, variance. Okay, these two terminologies are also get added along with these two. But overfitting we can prevent. Okay, we can prevent the overfitting by increasing the data, by taking the use of data augmentation. We can add the we can take the use of regularization concept. We can add the dropout layer. We can drop the nodes from the layer. We can use the callback mechanism, or we can use the early stopping mechanism in order to prevent the overfitting. Okay, underfitting we do not require. However, if we are getting the overfitted model, we have an option to handle the overfitting. I hope it is clear.
Yes, sir. It means like when we train our model with lots of features, there is a possibility of having overfitting, right?
Amma, oh, 1 minute. Someone is calling. Okay, just a second. Hello. नहीं नहीं नहीं, क्वेरी तो हो रहा है ना, चल रहा है, आप हो नहीं सेशन में? अच्छा, हाँ. Hello. Yeah. Am I audible? Participant, am I audible?
Yes, sir.
Hello.
You are audible. Yes, sir.
So I got a call from Sharma sir. Okay. So I thought.
Okay.
So that part is clear. Someone has asked underfitting and overfitting. Please acknowledge.
Yes, sir.
Okay. Okay. Any other question?
Any other query? So we move further in the session. Okay, thank you so much, sir, for such an interactive session. Knowledge shared by you is really appreciated, and I hope participants have learned many things from your session. Now, I would like to introduce second speaker of the day, Dr. Rohini P. We have with us. So we are delighted to have Dr. Rohini P, Assistant Professor in Department of Electronics and Communication Engineering at the Indian Institute of Information Technology, Design and Management, Kanchipuram. As a speaker for this faculty development program, Dr. Rohini academic journey begins with her PhD in biomedical engineering at the prestigious Indian Institute of Technology, Madras, where she joined the Non-Invasive Imaging and Diagnostic Laboratory in 2016. Her doctoral research focused on neuroimaging studies to uncover intricate variation in Alzheimer's diseases utilizing MRI, image processing, and machine learning techniques. Her thesis dwells into identifying textual changes associated with brain based Alzheimer trained, demonstrating her expertise in advanced image processing algorithm and brain imaging tools such as BSE, BET, BrainSuit, Neuron, SPM8, and MATLAB. Following her PhD, Dr. Rohini was awarded a pre-doctorate fellowship by IIT Madras to further her research at NIID Lab. In 2021, she joined IIT DM Kanchipuram as an assistant professor, where she established the Translation Healthcare Research and Innovation Lab. The lab focused on medical image analysis, for neurodegenerative diseases and biosignal processing projects. Dr. Rohini expertise in neuroimaging, medical image analysis, and translational healthcare innovative promises to provide valuable insights and inspiration to the participant of this FDP. Welcome, ma'am. Over to you.
Thank you very much for this warm introduction. Thank you. I hope I'm audible.
Yes,
Yes,
ma'am,
I'm
ma'am.
you are
audible.
audible.
Yeah, yeah. Okay, thank you. Let me just share my screen. I'll just start in a few minutes. Okay. Okay, so thank you very much. And in today's lecture, so I was intending to share a few basics, very, very basics of image processing and analysis, because this creates a backbone for whatever we are going to do next. Like, for example, you are going to work on deep learning, you're going to work on whatsoever next. This creates a basic backbone for all the techniques and technologies that they are going to develop. So I will go in detail. So I'll be taking another session tomorrow, which dives in deep into what we have already done based on neurodegenerative disorders and other things and cognition and other things. But today, let us just focus on a few. I mean, it's already 7:30, so everybody will be having dinner and other things. So we will just focus on the basics. We will update the basics clearly in our mind, so that when we are going to the application part tomorrow, it will be very easy for us to grasp it. Okay, so basically, why are we interested in these kind of disease diagnosis, and what kind of disease diagnosis are we looking at? So whenever we use any medical diagnosis, we go to a doctor, we take a consultation. So the doctor does a physical examination and he orders some tests, right? So these tests are broadly classified into three types. One is a blood-based biomarkers, blood test. We also have biosignal analysis, that is the doctor tries to take in some signals, some kind of signals from the body. That is, there are many different signals. We'll just come to it. Okay. And the other one is image analysis. So what are these signals and what are these signal analysis that we are looking at? So every part in our body, you name it, it has a particular signal, ranging from electroencephalogram, so brain waves, brain signals, oculogram from the eye, cardiogram from the heart. We have other kinds of respiratory parameters. That is, what is your lung volume? What is the oxygen intake per second? So all these things are important when a doctor is doing diagnosis. So he may not order all the tests, but relevant to your condition, relevant to your symptom, he will be ordering some kind of test. But these are the things that are already available, and some of you may be working with some of these signals, and maybe some of you would have encountered these kind of signals that are being taken and analyzed, right? And we also have the other kind of imaging modalities that are there in our system. So we start from X-ray. So it is very commonly available, very cheap, very, I will not say very informative, but the basic information that is needed for any quick diagnosis, we prefer going into X-rays, right? And we have CTs, we have MRI, SPECT, PET, and ultrasound. Let's go into detail. So I just want to give a different dimension to this image acquisition. So we always see image acquisition as a particular kind of methodology, right? So why are we doing this image acquisition? What is the physical reason of it? So a doctor generally doesn't order CT or MRI just like that, right? So he sees the cost for it. He wants to understand the what is happening inside our body, which we do not know, which we are unaware of. Like, for example, the doctor wants to find out some alterations that has happened in the brain. Okay, so does he always order CT and MRI? No, not really, right? So depending on what he wants to see, depending on what is available. So based on that, there is a differences that are being created in what we acquire. Okay. So now, what is the reason for doing an image acquisition? Mainly because of human vision systems, right? So a doctor can only see that much which is available outside of the body. But when he wants to go inside, we need to go for with some other technology, some other technique and other things. So any imaging system ranges from visible spectrum, that is from our eye. Okay, eye is also a visible, eye is also an imaging system. It's a very, very powerful imaging system. Okay, so it ranges from eye to even non-visible electromagnetic power spectrum. So we will go one by one. So we have with the eyes, we have visible with visible spectrum, we have light microscope. You are very much aware of this light microscopy. So anything that is optical in nature that comes under visible spectrum, right? So we have also beyond visible, we also have thermal images. This is also one more example of system that is providing you the differences in temperature, right? So temperature differences that make up that are present in our body, that can be imaged through thermal imaging systems. Now, so we also have other beyond a visible spectrum, we also have radio frequencies. So that which operate in radio frequency, the very best example for it is MRI. Okay, so what is MRI? Magnetic resonance imaging. So whatever our body is made up of completely different molecules, right? So different hydrogen atoms, oxygen atoms, and other things. So there are different molecules and atoms that make up our body. Now, can we extract some kind of information from these hydrogen and oxygen atom that are present in our human body? So that is where started the imaging using MRI technique. Okay, so I'm not going into depth with the image acquisition as such, but still, if you can relate to it, it is a very highly powerful tool. Okay, so beyond the reach of any X-rays, CT, and other things, even X-rays and CTs are powerful, but still they are categorized to be as an imaging system that creates even a small harm. Like it is not an invasive, but still it creates a certain harm to our body because of the use of the radiations. Okay, but these MRIs, they are very, very safe because they operate in radio frequency and they extract the information that is already present in our body, in the sense that whenever our molecules are having a particular spin, so they take note of these MRIs, they understand what is a spin and how much energy is being released from that particular area. So I am repeating again, I'm still not going into depth with MRI as it will take too much of time. But why I wanted to stress on this MRI is we will be seeing about this tomorrow in a very detailed way, like how these can be used for further processing and analysis and other things. But still, if you can see the basic difference between X-ray, CT, and MRI is the capabilities of the system. Like for example, X-rays and CTs are very much advanced to take on information about hard structures like bones and other things, right? But these MRI, they are highly capable of differentiating between the soft tissues. Like for example, in your brain, let us consider, mainly we use MRI for brain, but it is not restricted to brain, but we also can use in other human parts of the human bodies, like heart is also very significant organ which can be taken care by MRI. Okay, so basically why brain? Because in brain we have multiple types of soft tissues that are embedded together. Like for example, if you take different regions of brain, cerebrum, cerebellum, brainstem, cerebrospinal fluid. So all these things have different kinds of soft tissues, right? So we call them to be as gray matter, white matter, and other things. If you had a introduction to it. So when we want to image these organs, these sub regions separately, then there is a requirement of the imaging system to be highly capable of taking in that kind of information, which your CT and X-rays cannot do properly. So that is why we generally go in for MRI, so which will give a very good differentiation between the soft tissues that are present in the image. Okay, and in the body. The other other aspect of image acquisition is fluorescence. So we went for radio frequency image acquisitions. We have fluorescence microscopy, which operate in UV range. Okay, so we also have other kinds of X-ray frequency. So we have already seen this. So X-ray, chest X-ray, and head X-ray is we can take, which can be used um, uh, for many kinds of disease diagnosis. So why are we seeing about all these things? Because you need to we can gather a very good information that different parts. You can see here, this is the head CT. Okay, so the amount of information that is available in the head CT is different when compared to if I place a MRI of the same region. The amount of information that is available in the MRI is different. So this is why, as a previous speaker had concluded, that you can see multimodal imaging is very commonly used right now nowadays. Multimodal image analysis and other things. Why? Because the information that is available in one modality may not be available in the other modality. So to have an overview, to have a very good understanding of the certain things that are happening inside our body, it is better. Sometimes it is better to go with multimodal imaging aspects, and when a doctor requires that, they order for both CT and MRI. Okay, so it's good to have different kinds of image acquisitions. So the other one is PET. PET is a positron emission tomography. So this is also a 3D imaging technique, which operate in gamma ray frequency. So we can see from beyond the visible spectrum, we are going much ahead in the electromagnetic spectrum waves. So you can see, if you can remember the EM wave, the frequency, operating frequency of EM waves. So you can see each operating frequency has different kinds of imaging that have been developed, and it has been used. Still it is being used for different kinds of disease diagnosis and other things, right? Now, the important aspect of after image acquisition. Okay, so we have some kind of images based on different regions, based on different wavelength that are being given to our body. We have different kinds of images that are being acquired, right? So after that, what is the process that we need to follow? Is it that all the images that are being acquired uh, are of good shape and size? We don't know. We have generated some image, okay, based on some acquisition technique, we have generated some image. But is it good enough for further processing it? So how will you identify whether the image that you have acquired, whether the image that you have got, first of all, is good enough? So for those, we have something called to be as image quality assessment technique. So the very basic image quality assessment or signal quality assessment is a signal to noise ratio, right? Everybody would have heard about it. PSNR or signal to noise, SNR or PSNR, we can term it as either way. But what we generally measure is how much of information is present against the noise, correct? So is SNR or PSNR good enough to do an image quality assessment in the medical setting? See, now we need to understand one basic difference. Everything that we are doing in imaging, okay, so there are two aspects to it. As I told you, invisible light, that is invisible light, whatever we are seeing, we are taking a photo, natural scenery, right? So these natural sceneries have different backgrounds. Like, for example, different color spaces are there, right? So these techniques, most of the techniques, whatever we are doing right now, are all customized to, are all developed on these natural sceneries and natural images or natural objects, like, for example, any tree and other things, or even we can say everyday utility objects like cars. Object recognition models are based on cars and other things. But are they really good enough to be applied on medical images? So that is one big question that is still there. Okay, so but still we are trying to adapt whatever techniques that are being there for natural images or natural sceneries that are being developed to medical images. But what kind of modifications we need to do? How can we do it? So all those things we will be seeing in in this particular lecture. Okay, so basically, this is image quality assessment. So we will try to understand what I try to give you a brief intro about what is image quality assessment and how we are going to go about this. And we have other part of it called to be as image manipulation. That is, image manipulation is different from image analysis. Image manipulation means I can also term it as another word, image beautification, image enhancement, meaning I have a very dull image, right? So we take photos, we see that our images are very dull. So you apply a filter to it. Correct. So there are filters that are already available in your mobile camera. So we apply a filter to it. So what happens to the images? They get beautified, right? So what are we doing generally is we perform a convolution operation based on the filters, okay, and we enhance the regions of our interest. So that is what is called to be as image manipulation. Now, whatever I was talking about right now is based on purely images that are being taken in the real world. But medical images, can we use the same technique, same kind of approach for doing enhancement in the medical domain? We will see about it, right? So, and what about image analysis? So, there are different techniques to do image analysis. So, first of all, we will go into detail about image analysis in the coming slides. And after doing all these things, so this completely take up the image processing and analysis part. And the other two aspects of it is displaying. So displaying is also a very, very important thing, because once if it is not displayed, all the images are taken in the form of matrices, right? So we have numbers. It's just made up of numbers. So if you don't have appropriate display unit, okay, or displaying technique, I will say. So it is also an algorithm. So how we are using some algorithm to convert the numbers into some visible, understandable and visible image. Okay, so that is also an important tool, and image perception is also an important tool. So how we perceive a particular image. So all these processes make up the entire set of image processing and analysis part. Okay, let's go one by one. So what is the need for image quality assessment? Okay, I had already told you. So now, you can see these images. Okay, I have given you 5 images. This is nothing but a laparoscopic image. So if you can understand the laparoscopic technique is nothing but I have a small camera, okay, that is sent into my body using a tubular structure. Okay, so we have some kind of, you can think about scissors. So it will be like kind of scissors, but a very long scissor through which, towards the end of which you have a camera and some tools that are needed to operate on some organs. Okay, so they make a small hole on your body and they insert the tool for getting some images and doing some operations, so some surgical technique, or even to image what is happening inside the body. So both are possible. Now, I have showed you 5 images here. Okay, so you can see this is a very nice representation of the whatever is there inside the body. Very nicely it is being represented. But you can see in this image, it is actually fogged, right? So what happens is whenever we use any laparoscopic images, laparoscopic during the surgery, we do some kind of cauterization. Cauterization means some cutting and heating will be going on to stop the bleeding from the tissues, or some kind of tissue removal will be going on, so that the some tumors or some kind of extra growth in the organs will be removed. Okay, so for when they are being done, smoke will be released as a byproduct of these activities. So these smoke, what will happen is it will hinder the view of the surgeon. So you can see this is a very highly corrupted image, right? So that is being captured from the laparoscopy. Now, if I'm using this image for analysis or this image for analysis, which will be better? Obviously, this will be better, right? So we need to understand whatever image we have acquired is good enough to proceed with the analysis technique. So for that, we have something called as image quality assessment techniques. There are many techniques that have been used and still they are being developed for getting the assessment, for assessing the quality of the images. As I told you, the basic one is PSNR, but still we have BRISC technique, which is standardized. But whatever technique I'm saying you now is all meant for natural sceneries. Okay, so in natural sceneries, we don't have only few color spaces. You can see this, the color space here is very, very limited, right? You have only, most of the things are red in color because of blood, and some yellowish and tint of orange is there. That's it. So it is almost, we can consider it to be as the monochromatic images. So there are very limited variation in the color space, right? But this is not the same case when we look at the natural sceneries. Natural sceneries have different kinds of color spaces, or even if I say grayscale values, even if you take a black and white image, or I will not say black and white, I will say a gray space, that is inverted image, negative image. Okay, so in that also you will have a very high contrast between. So next we are coming to contrast. Okay, so we have a very nice contrast between the different objects, but that is not the case in medical images. So there is a need to develop image quality assessment techniques that are very particular to the medical imaging space. Okay, so this is one area that we are working in, and we have found out certain techniques that are highly suitable for medical images. Probably I'll share some of the results in the next class, because today I am planning to cover only the basics. So we will go about each specific case study tomorrow in the tomorrow's lecture. So I will give you some information, some idea about how we can go forward in this area and understand how image quality assessment can play a vital role in further image analysis. Okay, the next one is about image contrast. So what is contrast? Contrast between two objects. Now, if you can see this, okay, these are the two images that are placed side by side. Okay, so inside is the foreground. This is the foreground of the image, and this is the background of the image. If you can see the pointer movement, so this is the foreground, the inside square, and the outside square is the background of the image. Okay, now if you can just see the inside square. Okay, this is the first image, this is the second image. If you can just see the inside square, can you see it? So both the inside squares are having the same gray level. Okay, and now if you can just see clearly, carefully, you will be able to understand that both the gray levels are similar. Whereas, which image is highly visible, which image has a very good visibility? The second one, right? Why? Because the background information present in the second image is comparatively having a very huge gray level variation. Okay, so if you can see, if I consider this to be as the foreground to be as 200, okay, and the background to be as 150 in the first image, in the second image it is almost 0. So the difference between the background and the foreground is very high in the case of the second image when compared to the first image. So that is what makes up the contrast. The contrast is always taken in terms of the difference between the background and the foreground information. Okay. Now, to get a more clear idea about contrast, you can see this image. Now, you can understand the term contrast. So, this we call it to be as just noticeable difference. Okay. So, what is this just noticeable difference? You can see the 5 square rectangles here inside a big square. Sorry, big rectangle, right? So the background is there. Background is, you can think about it as some 150 gray level or something. But if you can see the foreground, I am having a variation in the foreground, you can see. Now, at which point, at which point there is a just noticeable difference happening between the foreground and the background. Okay, so that is what is called to be as a just noticeable difference, where you can see only, I mean, after, if I keep the foreground value beyond this, that is before the, I mean, it is having a slight increase in the gray levels towards 1, towards 255, right? So it is becoming white. So if I still decrease the gray level value, it will merge with the background, and I will not be able to see the difference between the background and the foreground. So that is what is called to be as just noticeable difference. So when so why is this image contrast important? So what are we looking at by understanding the image contrast? When we see inside the human body. Okay, so most of the things that we are going to image will be in grayscale. It will be like either shades of gray. Okay, so when can I notice the difference between two gray levels? At what point can I notice the difference between two gray levels? That is very, very important. So this is also dependent on one more thing that is called to be as gray level resolution. So what is gray level resolution? The difference between the two structures or the two regions that are being imaged are understandable or are identifiable. That is called to be as gray level resolution. Okay, so that is very, very important in terms of image contrast. When our resolution is very good, our contrast will also be good. Okay, so how do you fix that resolution? Now we know our basic, all our images are made up of 8-bit resolution. Why this 8-bit? Because it is a standard that is being used in natural photos. Again, I'm telling you, in your images, whatever we click in photos, okay, that makes up 8-bit resolution, meaning I have values ranging from 0 to 255. Okay, so why this number 255? 2 power 8. Okay, so 2 power 8 is 256. So the value ranges between 0 to 255. Now, what happens in most of the imaging systems is, as I told you, in our body, whatever imaging system is getting to reproduce is are will be in gray levels. It will be in grayscale. Okay, in different values of gray. Um, we may encounter certain problems when the difference between a normal tissue and the tumor tissue. Okay, if we can think about normal tissue and tumor tissue, the difference between them will be very, very, very less. Like for example, in CT, if you take, we measure the difference, we measure the, how will I say, we measure whatever that is coming out of the imaging modality as Hounsfield units. Okay, so these Hounsfield units will be very, the difference between the Hounsfield units between the normal and the tumor tissue will be very less, wherein 8-bit images will not be able to capture that difference. So what we generally do is, in imaging systems, especially in medical imaging systems, we go in for 16-bit resolution. So 16-bit means you can think about it as 2 power 16 values will be used to represent the gray level variations. Okay, so I will have values ranging from 0 to 2 power 16. Okay, so 2 power 16 minus 1, because 0 is included, 2 power 16 minus 1. So that many values we will be using instead of 0 to 255 to image the organs. Okay, generally we use in CT, in many optical microscopes also we use 16-bit resolution. Why? Why it is used? To improve the image contrast. Okay, now so I had told you image contrast is very important. Image assessment, image quality assessment is important. The how do we improve the image contrast? Okay, so there are many techniques that are being used for pre-processing the images. So overall, the techniques are called to be as overall technology or pipeline. I will call it to be as image pre-processing pipeline. Okay, so it may include not only one updation, rather it may include a range of updations. Like for example, from image contrast enhancement, noise removal. There may be noises that are present in the image. Noise removal will be there, and registration. So we'll talk about registration in the next lecture. That is what kind of registration techniques are there and other things. So these are all major techniques that we include in our pipeline for pre-processing. So one example which I want to give you is, you can see here, this is a image of a cell, okay, that is actually present in the, that is being imaged through some optical microscopes or electron microscope. I think it's a electron, SEM images. Okay, so it is an electron microscopic image, and this is a cellular image. You can see it's made up of different cells that are present. So slide image. Okay, now if I compute the histogram of this image. So the first thing, that whenever you have an image ready, okay, after acquisition, after assessing the quality of the image, the first thing that you need to do is you check the gray level, the range of gray level that are present in the image. So if I check the range of gray levels, for example, I plot a histogram here. Okay, so I plot a histogram here and I see, you can see this is the histogram of this first image and this is the corresponding histogram of the second image. Okay, now this histogram is having a very narrow range, right? So maximum, most of the pixels are in the range between what is that, 75 to I will say say 100, that's it. So almost most of the pixels are present in between 75 to 100, and very few pixels are present after 100. Okay, but wherein you can see this image where the pixel range lies from, it starts from 100-ish to about 250. Okay, so the range is quite high when compared to the first image. Okay, so I'm talking in comparison only. So here nothing is actually fixed. In any kind of image processing, you need to understand everything is relative. Nothing is fixed. Okay, so here the difference is about just 25, whereas here you can see the difference about 150 in the gray level variation. Which is better to look at? This one, obviously, right? And why the image contrast is very good here? Because of the background. The background is white, whereas the foreground is almost having all black regions. So it is highly distinguishable, whereas here the background is also grayish in color, and whereas the foreground is also having a shades of gray. Okay, so the even though the edges are having a very high differentiation, but still understanding or analyzing this image is quite difficult when compared to this image. So now, what kind of pre-processing can we do? So the first very basic pre-processing technique that we can think about is histogram equalization. So what is this histogram equalization? Sorry, yeah. So whatever histogram we were having here, right? So this is having a very narrow range. So what we are trying to do is we are trying to expand this histogram into to occupy the almost all the gray levels in the present in the image, right? So what we are trying to do is, you can see here, this is the original image. The original image is having black background and some grayish cells are there. That is very, very, very narrow. I mean, that is very, very gray in color. So very close to zero. And this is the original histogram of this image. Okay. Now, what we are trying to do with histogram equalization is, you can see here, I have expanded this histogram to fit from 0 to 255. You can see this. So it is uniformly distributed. Okay. So this technique, what it does is, it tries to occupy the entire range of the gray levels that are present in the image. So now you can see the histogram equalized image. You can see what the cells are highly distinguishable from the background. But what is the disadvantage here? The problem is, yeah, good enough. The cells are highly distinguishable. You can see so much of noise that is being added that is not at all available in the original image. Original image is very good actually, right? So what has happened is, in the process of enhancing the image, what we had tried to do is to introduce noise into the image. That is because of the methodology that we have followed. Okay, so what I want to tell from this, so I'm all, see, it is not only that all the techniques are good. So some techniques are good for some kind of images, some techniques are perform very poor in the same scenario. So whenever we are looking at these kind of medical images, okay, it is better to go with by trying out different kinds of techniques that are available, and identifying why the technique is actually performing well, because only then we can go in the advancement of these methodologies. Okay. So the next thing that we can think about is Clahe. Okay, Clahe is also an adaptive it's also a histogram equalization technique, but rather than having the entire histogram to be equalized, what Clahe does is, it will take only certain part of the histogram. So for example, this is the histogram. It will take only the certain part of the histogram, and it will try to rearrange the pixels in the lower end of the, in the bottom of the histogram, so that it equalizes the histogram in a adaptive way. Okay, so this is also called to be as adaptive histogram equalization technique. But there is also one more thing that is called to be as contrast limited. So here that contrast limited is actually playing an important role. This particular technique, actually what is the advantage of this technique is it avoids the problem of over enhancement. So what is this over enhancement that we faced here? So this has an over enhancement. You can see the other regions which are actually not at all in the original image, it has also showed up, right? So that over enhancement is avoided using when we are using this histogram Clahe based techniques. Okay, so I have given you an example here. This is a eye image, retinal fundus image. Okay, so it is given as an input to the system. You can see when I'm using a histogram equalization, you can see the difference here. So all the minute blood vessels are actually enhanced and it is shown, right? So these are the minute blood vessels that are there inside the eye, and they are enhanced and it is shown. Whereas when you use Clahe along with better, it is actually the blood vessels are better than the histogram equalized image, but you can see, as you can see, there are also noises that are being introduced along the image, right? So what is the conclusion of this? So you can see the histograms here. So this is a original histogram. Okay, and when I use a histogram equalization technique, you can see how the histogram is modified to occupy the entire range. Here also we are actually using in Clahe also we are actually using the entire range, but how the redistribution happens. Okay, so here it is just redistributed to occupy the entire range of the histogram gray level values. But here how the redistribution happens, that is varying. Okay, so this was introduced to understand the adaptivity, how the adaptivity will play an important role in histogram equalization. Now, there are other techniques also. Okay, so I am just concentrating on the basics. I will try to give you a case study based scenario so that it is very helpful for those who are working in this domain. Okay, and what kind of the next aspect of it is noise removal. Okay, so when we use these kind of histogram equalization techniques, obviously noises are there, noises will be arising. So also there are inherent noises from the image acquisition that is also being there. So what kind of noise removal techniques we can use to remove the noise that is present in the image? Okay, so image averaging is one of the very basic um, technique that are being used for noise removal. So what is this image averaging? So what I do is I take multiple images, okay, of the same region, okay, of the same region of interest, and I average over those multiple images. That is, I stack all the images together and I take the average of all the images. That is one way of doing the image averaging, right? The second way of doing is spatial averaging, meaning I average over a particular windowing. Okay, over a particular window I take and I average it. So that is a called to be as spatial averaging technique. So here you can see so there are two ways, ensemble average and spatial average. I have given you some examples. So you can see these are the images just to understand what is image averaging. Okay, so these images contain different shapes. You can see circle, square, different triangles are there, different small triangles are there and other things, right? So we are seeing how the noise, this is a noise affected image. So in this, I've added some noise, basically Gaussian noise. Okay, now these ensemble averaging methods, okay, that is ensemble average or spatial average, how is it going to perform on these particular images? So if I average two images, how it is actually going to remove the noise, or how it is going to actually enhance the information that is already available in the image. So you can see if I average across the multiple images, you can see I have averaged twice, thrice, four times, and finally you can see the ensemble averaged image that is actually looking very similar to whatever the original image was, right? So as many times as you average, as many number of images you take for averaging, your obviously the noise is going to remove. So okay, so this is one technique. The second one is about one more thing that is very important is in the image averaging we also use some kind of filters, right? So we use there are different kinds of filters that can be used. They depend upon the neighborhood that we are going to select. So this is called to be as neighborhood operations. Okay, so what kind of neighborhoods can we select? There are multiple kinds of neighborhoods. This itself is one research topic. Okay, and all these things which I am telling you right now is not only for image processing operations. Whenever you go for deep learning, okay, this is the same thing that you're going to implement there also. You are writing it in one line, but rather if you go in depth in the what is the mathematics behind these deep learnings, convolutional layer, convolutional networks. Okay, so they exactly do the same thing what basic image processing does, correct? So this is a 3x3 square, okay, and I'm going to overlap this 3x3 square on the image, and I'm going to do the neighborhood operation, meaning for example, I want to understand, I want to do a averaging here. Okay, I want to use some kind of filters for doing an averaging. So I take a 3x3 patch here. Okay, and I use the information that is available in the 3x3 patch, and I convolve it. Convolve it means nothing but you do a pixel wise multiplication throughout the for all the pixels. Like for example, you take a 3x3 patch means you have 9 values here, correct? So for those 9 values, you do dot multiplication, that is pixel to pixel multiplication, and you sum all the values, okay, and take an average. You do whatever you want, but that is the operation that is being done. So a convolution is nothing but you do a pixel to pixel multiplication and a sum. Okay, so that operation can be used for multiple purposes. Okay, but basically, what kind of neighborhoods to select? So you can take 3x3. You can take a square of 3x3. You can take a just the 4 immediate neighbors, okay, to the center pixel. You can take only 3x1 bar, a vertical bar, a horizontal bar. You can take 5x5 neighborhood operations. So why these many kinds of different neighborhood operations are preferred? Okay, if you can remember the convolutional network, right? So you had one point written there to be as the kernel size. Okay, the kernel size is equal to 3 or 3x3 or 5x5. That is the same thing that we are trying to bring here also. What is the difference between 3x3 and 5x5? Why do we need to use that 3x3 or 5x5? Basically depends on your image size. Okay, so your image resolution. Now, if you're taking a image, a photo of any natural scenery, you can think okay, for example, let us take two mobile phones for this case. Okay, I am taking two mobile phones and I'm planning to image the same scenery using those two mobile phones. One mobile phone is having a very poor resolution, and the other mobile phone is having a very high good resolution. So what do you think is, from the very low resolution image, the image size will be like, for example, 100x100. Okay, the same area. Okay, I'm taking the same region, I'm taking the same area with a resolution of 100x100. Whereas the other mobile that is going to give me the same image is having a very high resolution. Okay, so for the same image will very high resolution means it is being represented by a higher number of array. Like for higher, like for example, let us consider, for just for the sake of understanding, let us consider it to be a 1000x1000. Okay, now you think about it. I have a 100x100 image. I have a 1000x1000 image of the same scenery. Okay, now should I use a 3x3 neighborhood operation to do any convolution, whatever you want, or should I use a 5x5? It depends on your image size. Now, for example, if you want to work with 100x100 image, it is better to use a 3x3. It is better to take a small neighborhood and then go on doing the operation. If you are having a 1000x1000 image, so it is better to take a 5x5, because the same information that is covered by 3x3 square here in 100x100 image is similar to whatever the 5x5 square is going to consider in the 1000x1000 image, right? So it depends purely on whatever kernel that you're going to select. It depends purely on the size of the image. So what I would suggest you is, before going into any kind of image analysis, please understand your image better. So understand what is the information that you want to extract from the image. So when you understand those aspects clearly, then you will know what operation to use. Okay, you will know what kind of filters that you are going to use. Okay, now you can similarly you can take a cross, vertical, horizontal, 5x1, or you can take multiple shapes of kernels. It need not be only square. It can be different shapes, like as in that is given here. Okay, each one has a particular advantage over the other. That and this depends on the imaging. Sorry, the images that are under consideration also. Okay, so now, okay, one idea here is you can see here. I have taken a small example here. This is the original image. It is having a 500 cross 500 pixels. Okay, and these are the images that are being filtered. Filtered means I have used a 3x3 filter. Okay, so this is a 3x3 filter, a kernel. Okay, and I have used them on this 500 cross 500 pixel image, and I have done nothing but averaging operation. So what is an averaging operation? You take this 3x3 patch, you dot multiply each values, okay, by 1, you dot multiply it, and you take an average of all the numbers that you have done, and that average value will be replaced in the center pixel. Okay, so this is the averaging, basic averaging only. Okay, so now if you see this, there is so this is a 3x3 averaged data. Okay, and this is 5x5, 9x9 filter. Okay, so this 5x5 is this one. I have increased the filter size 9x9, 15x15, 35x35. So now what happens, you can see here the small details that are being there, it's being reduced. You can see the A here is not visible very clearly, right? It is very sharp here. It is not very visible here. Here you can see the A has completely disappeared, right? So what is happening, this is the same thing that I tried to explain there also. So the kernel size need not be always 3x3, not necessarily. So always we use, even in medical imaging, we generally by practice we use 3x3. It is not necessary that you need to use 3x3 always. It is fine to use 5x5 also. Okay, but depending on which situation you are there. Okay, what is your image size? What is the information that you want to extract from that image? So depending on all these things, you will have variation in the size that needs to be considered. Okay, so this is one of the example that I will give you. So in the 3x3 median filter, okay. So if I use a 3x3 median filter over a noisy image like this, you will have a very nice noise removal that has been done. So you can see noise removal is being there, and you can get back the original image. Whereas if you use a averaging filter, so this is the image. So you can see this is actually a Gaussian noise image. Okay, this is a salt and pepper noise. You have sudden spikes in the images. Okay, this also occurs due to thermal variations in the imaging systems. Okay, so when the thermal systems are heated up, you will get abrupt noise patterns that are being introduced into the image. Okay, so you also have Gaussian noise, and along with the images that are being acquired. Okay, so that can be removed using an average filter. So like this, you can do multiple things with the filters. So this is just an example, very basic example of mean and median filter. But if you can think about these things, the same is actually implemented in deep learning also. Okay, but in a hidden way. So we are using filtering only. We are doing some kind of operation on filtering only, but it is just given in a hidden way that we need to understand. So how these convolution layers can help in removing noise and extracting features. So both are being done at the same time. Okay, we will just come with the imaging deep learning network also. I will just give you an introduction for deep learning networks also. Okay. So other than this noise removal in spatial domain, we also have some kind of frequency domain approaches. Okay, so what is the frequency domain approaches? So we can transfer the image into another domain, which is called to be as frequency domain. You can see this is it's a phantom actually. Okay, so this is a very basic example of a phantom that is being imaged using CT. Okay, so we have used CT to image phantom that has some holes here. Okay, so phantom is nothing but agar phantom. Okay, so we have some holes here, and this is being imaged using CT. Now, when I take the Fourier transform of it, okay, so what is Fourier transform? It's basically converting the spatial domain into a K space, right? So K space is nothing but it's a frequency space. So the center is 0, 0 frequency generally. Okay, so we take from the center because of negative aspects. Let us not go into details about it. So you can think about an imaginary cross here. Okay, an imaginary cross. So the center of that cross is 0, 0, and this is a increasing range of frequencies in the u direction and the v direction. That is horizontal direction and vertical direction. Okay, now if you can see, this image has a frequency domain spectrum of frequency image of like this. Okay, when some kind of noisy patterns are introduced into it, like for example some kind of lines, you can see horizontal lines are introduced into this agar phantom, right? So now if I use this, okay, and if I image it, if I image this, and if I take a case space of this, you can see this spectrum is being transformed to like this. What is this? It is having some noisy patterns that are being introduced into the image. Correct. So what I'm going to do here is, I know that these horizontal lines are there, right? So they correspond to a particular frequency that is being mapped like this in the vertical direction. And these lines are being introduced, right? So what I'm going to do is I'm going to remove these lines from the K space. You can see I've just made it to be 0. Okay. And I'm going to reconstruct this image back to the spatial domain. So this is K space. I'm going to reconstruct it back. Now you can see the horizontal lines that are there that are slightly disappeared, right? So it is actually normalized now, and these dots are visible very clearly rather than what is being visible here. So this is one of the approach that we try to do in frequency domain. This is basic Fourier transform approach. We can also do the same thing in wavelets. Okay, so discrete wavelet transforms, they use these kind of techniques to remove the noises that are present in the image. Okay, so now here we have all the frequency information that is available in one domain. In wavelets, what we generally do is we take multiple levels of frequency into consideration, and we try to extract only that frequency information and remove all the rest of the things that are not necessary for us. Okay, so okay, this is all fine. What is the main thing what is the problem in the frequency domain approach? What was not there in the spatial domain? Here we need to know the basic idea about what frequency we are interested in, correct? So we from here you can see this is a control image, right? So the original image, and for the original image I know that this is the frequency that I am interested in. Okay, that is why we try to remove these extra frequencies that are there that are occurring due to this noise. But when I don't have this original image itself, this is not available. These two images are not available. I have only this image. So how will I know whether these are not noises, whether these are noises or not noises, but information that is present? So I don't know, right? So any frequency domain approach has a very it's very good. It's actually a very good approach, but it also has a drawback of having to know what prior information that is available based on the prior information that is available. We need to do the process. And the second thing is it is also time consuming when compared to spatial domain, because when you want to implement all these, so whatever we think about image processing, image analysis is we want to implement into a server, or nowadays we are moving towards highly technology driven practices, right? Telemedicine, everything is in tele only nowadays. No direct interaction. Everything is through video call. Everything is through communication transfer. Okay, so these things happen to introduce noise, and the frequency domain approaches try to enhance these noises that are present in the already present in the image. Okay, so that is why we, as much as possible, we try to work on spatial domain itself, but these are also available. I just want to give you an idea that these are also available to use in the for many kinds of image analysis. Okay, but as a pipeline, it is better to stick on to spatial domain approach rather than going into any frequency domain or transform domain approach, I will say. Okay, transform domain approach works better when you don't have to reconstruct the original image back like this. Okay, so if you want to work only on this, if you move to one transform, one domain from one domain to another domain, it is better to keep the information in that domain itself and work and do some prediction in this domain. Okay, if you again transfer it back, then there might be possibilities that your image gets corrupted and other things, so which will create unnecessary problems in the image analysis. Okay, so this is one more thing. The other basic idea is about edge detection. So what is the edge detection that, why do we do this edge detection? Now, when you think about this edge detection, this is the same thing that your CNN does in the convolutional layers. Okay, so it actually does edge detection only, but we don't know that it is doing the edge detection. Why? If you can think, I don't know whether you got an idea about CNN or not, but this CNN has convolutional layers, right? So when you pass on from one layer to the other layer, it is actually multiplied, or I will say convolved with some kind of filters, correct? So those filters are what? What are those filters? You would have never seen those filters in your, whenever you're doing an implementation, correct? So like for example, if I take a 100x100 image, after passing on to the first layer, first convolution layer, this 100x100 image will become 100x100x32. Where did that 32 come from? No, I mean, we will not have an idea about that 32, right? So what is this 32? What they have already done is 32 filters they would have designed. Okay, so based on what they would have designed filters, based on whatever we are already doing in image processing. Simply doing an edge detection, horizontal edge. I need to detect a vertical edge. I need to detect a slant edge. So these edges, it is not only edges, but I'm just giving you an idea. Okay, so edges, texture details, different kinds of information that can be put under a kernel perspective. That is only being compiled as filters, as a number of filters. So at each level, after each convolution layer, the size of the depth of the image keeps on increasing, right? Because of this only. Okay, so what are the basic edge detection techniques? Okay, so whenever we talk about edge is nothing but change in from one gray level value to the other gray level value. So here you can see this is a same square image, but why I had taken square image means it's good to sorry square, I mean the shape image. Okay, so it's good to understand the different role of edge images, okay, edges in the image. Okay, so right now when you look at these shapes, you transverse from one in one direction, you go from left to right. You can see whenever there is a change in the gray level, it is called to be as an edge, correct? So when I have a profile of edge, it will so when you consider a real-time image, meaning that these are all simulated images, correct? But when I take a real-time image of your photograph or of any medical data, okay, so if I take a real-time image, the profile of the edge will not be will not be like this. Basically, it will not be having a sharp variation. Rather, it will be a slant. It will be an increase. So from when you transverse from one direction, so you will have a slight variation in the edges, and it will go to the other foreground and come back to the background. Okay. Now, when you do this, this is your when you have these kind of edges. If you do take a first derivative, okay, what is the first derivative? First derivative is nothing but difference between two pixels. That's it. You when you transverse from left to right direction, okay, you continuously take the difference between the pixels and you get it as an image. Okay, so that is what is being done here. Okay, so you continuously take the difference between the image and sorry, difference between the pixels, and you mark it as an image. So that will give you a first derivative image. Okay, so what happens is only the edges, you can see the positive edge and the negative edge, the rising edge and the falling edge is there, right? So at those points, you will have a variation. So this is the first derivative. And if you take a second derivative here, you can see here, during the rise and fall, okay, with respect to edges itself, that is, the starting edge and starting point of the edge and the end point of the edge. At those places, you will have find impulses. Okay, so this is a second derivative. Now, you can see I can have horizontal edge detection, I can have vertical edge detection, I can have depending on the filter that I am going to design, I can have different kinds of edge detection that can be made possible. Okay, so you can see these are all vertical edges that are being detected. So for these vertical edges, you need to have a filter that can detect the vertical edge. So we can design a 3x3 filter. There are already pre-designed filters that are available, but if you want, you can design a filter which can detect vertical edge. That is nothing but it will find the variation in the horizontal gray level values. That is 101, sorry, 1 minus 2 minus 1. If you want, I can share that also in the next class, whatever filters that I have not purposefully shown here because that goes into too much into depth with the techniques and other things. So you can design a horizontal filter, a vertical filter, or anything. So this is a vertical filter. This is a horizontal filter. You can see white are represented by horizontal edges are represented in white color. Okay, so horizontal filters, vertical filters, and you can also have diagonal filters that are being designed. So that will also give you a information about what kind of diagonal lines are present in the diagonal edges are present in the images. Okay. Now, the second aspect of it is segmentation. So what is segmentation? Now, till now we have done pre-processing, right? So the next thing is about segmentation. Whenever we do any segmentation, now, this is very important because you need to, when you're using your deep learning. So nowadays, many people are working with deep learning, but it is not that when you're working with deep learning, image processing is of no use. Only if you know image processing, you can go with deep learning. If you don't know image processing, deep learning makes no sense. Okay, so when you do a deep learning based segmentation, many students, whoever I encounter with, if they are not aware of image processing, I can for surely see that they are not understanding the basic concepts of deep learning. That is what is being observed. So what I am suggesting is when you going for any deep learning based segmentation, because that is the state of the art, that is what we are working on, but still when you are looking at segmentation in image processing perspective, it also gives you good results. It is not that it is not giving you good results, but why we are going into deep learning based segmentation, we will just come in a bit there. Before that, whenever you do any segmentation, you need to have two things in hand. Okay, original image you need to have a mask. Okay, a mask is always a binary image. What is a mask? It has regions which you want to segment out as ones and the other background as zero. Okay, so you can see here, these are all the regions that I want to segment out. So they are all marked with one. Okay, and these are all regions that are being that are background. They are all marked with zeros. In another case, we may not have a single region, correct? In the sense, like, for example, these are the regions that are there, but these are all not connected, right? So this region is separate, this region is separate, this is separate, this is an individual region. You can see there are multiple individual objects that are present in an image. So we generally, whenever we go about segmentation, if we have multiple regions that are being that needs to be segmented into different classes. Okay, meaning you think about brain. Okay, in brain I have cerebrum, I have cerebellum, I have brainstem. I want to segment these into three different regions, not as a single region. Okay, then what you generally do is you give different labels to those regions. So you give cerebrum as 1, cerebellum as 2, and brainstem as 3. So you need to have this as well as the label information. Okay, if you have a single class, if you have a binary segmentation, that is 0 and 1, or if you have a multi-class segmentation, that is nothing but 0, 1, 2, 3, how many ever classes you want. Okay, so here it is being represented using 30 classes. You can see this is also possible. It is not that it is not possible, but it is complicated. That's it. It is a possibility that you can do, but it is a complicated task. Okay, now what are the basics of segmentation. I am just going to go I mean go through this in a quick way, okay, because this has already been we will be having these kind of idea based on basic image processing. So you can see the basic segmentation, image segmentation has thresholding and binarization. Okay, that is a very basic thing that we do. What it does is it whenever you have an image, I had told you, right? So the first thing that you need to do whenever you take an image is you understand the histogram of the image. Okay, so what this thresholding does is it segments the histogram into two different regions. One is the background and one is the foreground, or I will say darker object and the brighter object. So how do you do it? You can either fix a threshold based on the histogram. You can see the histogram and you can fix a threshold based on this. You can segment the objects, or you can go in for other thresholding techniques. One is very commonly used, global thresholding. Otsu thresholding is also very commonly used. Okay, so still now, so this is actually, it was introduced in 1960s, but we still use Otsu thresholding, right? So because it gives good results. Now we have different adaptive thresholding techniques. We have multiple kinds of advancements to the thresholding techniques, which adapts to that particular image. So all those things are available now, but still Otsu is very good to use. And this is nothing but Otsu is also, here we have to manually select the threshold, whereas in Otsu's method, based on the histogram, it automatically selects the threshold values and it gives us. Okay. Whereas we also have other kinds of technique that is called to be as region growing methods that are based on, but this is actually a semi-automatic technique. I mean, initially when it was introduced, but we can actually use it as an automatic method. We have worked on these kind of techniques, how to automate, how to automatically find the seed point and use it for region growing. So I'll give you a case study based scenario in the next lecture. Okay, but still, the region growing techniques are widely used for if you have uniformity in the region that is present. So if you can see this, you can see this is a white background and these are the cell images that are there. Okay, now if I want to segment the cells individually, okay, I can use region growing technique for segmentation. You can see this is actually segmented into multiple cellular regions. Now, what is it? What is the problem here? Good enough, it is segmenting the cell. But if I want to segment the nucleus, sorry, if I want to segment the nucleus, is it possible? Yes, it is possible. But how many seed points do you try to introduce? How many seed points do you try to keep? So that is very difficult. So it depends on the image in hand, what technique you are going to use. Okay, so it is not that you have multiple segmentation techniques. You can use all of them for doing a segmentation. No. Depending on what you want. In this image, if I want to segment the cell, okay, fine, region growing can help. If you want to segment the nucleus, probably yes, probably no. Okay, it depends on how you want to implement it. So depending on all those things, you need to select the method. Okay. And one more thing, the same thing applies for deep learning also. So whatever you are doing, it is not only in image, if you do properly in image processing, the same thing, you will have an idea on how to convert it into a deep learning method or methodology. Okay. So all these techniques play an important role in understanding the image analysis perspectives, image analysis pipeline. Okay. Now, you also have k-means clustering. That is also possible to segment the image. You can see what k-means clustering is. We have different image. I mean, different aspects of the images being extracted and plotted into the feature space. Okay, and you try to cluster the feature spaces. That's it. That is all is k-means clustering. You can see this forms a very nice cluster and this forms a very nice cluster. This is the background and this is the foreground. So you separate these two clusters and you image it, then you can get a very nice segmentation. But still, this is a very simple way. We also have different kinds of clustering techniques, FCM based clustering technique, which are soft clustering based techniques. So soft clustering is good enough to get a overall perspective in the image. Like when we want to specifically when we want to segment multiple objects, okay, we generally go for soft clustering methods because we need to we don't know how many classes are there in the image, right? So it's better to use soft clustering rather than a hard clustering technique always for segmentation perspective. Okay, so I'm not talking about classification here. This is segmentation perspective. Okay, now the next important thing is feature extraction. You will already have an idea about feature extraction, but still, uh, what is a feature? To explain it in a very naive way, we can think about what are eyes perceive, right? So if I'm looking at an object, I can see the smoothness of it, right? Whether the object is smooth or not, whether the object is rough or not. How are we able to distinguish between that? Our eye has a capability of understanding the smoothness, roughness, the homogeneity, all the other things that are present in the object, correct? So this is the same thing that we are going to translate where what our eyes does. Now, you can extract infinite features from an image. Infinite, I mean infinite literally. Okay, so you can extract infinite features from the image. So what is important? Extracting discriminative features is important. What is meant by discriminative feature? A feature that can differentiate what you want. What you want is, so for example, I'm taking color as a feature. Okay, I cannot differentiate an apple. Sorry, let us consider an orange. Okay, a green orange. Oranges can be green in color, right? So the native orange varieties and the sweet lime. Sweet lime is also green in color. So okay, so I cannot distinguish just by using color an orange and a sweet lime. Correct. So similarly, I cannot just use shape to distinguish these two. So discriminative features are those which can differentiate what you want. Okay. So for example, if you take a normal tissue and a tumor tissue, if you take shape as a feature, probably not. A normal tissue can also have an irregular shape. It is not that only tumor tissues have irregular shape, right? So shape cannot be a feature. So what can be a feature? Probably texture. Yes, possible. Because tumor tissues have inhomogeneous textures. That is, it may be, it is made up of too many cells cluttered together, right? So a tumor tissue is actually having a high concentration of cells, high concentration of blood flow. So it will be having a high variation in texture when compared to the normal tissue. So you can consider texture to be as one of the image. So one of the feature. Okay, so like this, depending on the types of features that are being extracted, that is, if you can extract structural information, texture information, color information, what is going to differentiate your the different aspects between the images that you are being analyzed. Okay, so that gives you the information about different variations. Okay, now you can see these are the different textures that are available. You can see how many textures are there. Okay, structured textures are there, asymmetric textures are there, pseudo periodic textures. You can see there is a periodicity here. So these are all called to be as pseudo periodic textures. There is a structural information that is available here. So these are called to be as structured textures. So there are different kinds of textures that can be extracted and analyzed using the texture information. So like this, you can, these are all shape-based features. You can see what is the size of a circle that is being fitted into the object? What is the size of a polygon that can be fit into the object? So all those information will be essential for understanding the shape of the object. So shape-based features, texture-based features, color-based features, all important. And the aspect, this is the same thing that you are actually extracting in the CNN. Okay, so
कुछ नहीं
the
चढ़ेगा
CNN,
तू ना हर वक्त रीच ना जाता है चढ़ा कुछ नहीं है हमें नहीं पता तो सोचता मैं
am
ऐसे
I
करके बहुत अच्छा कूल लग रहा हूँ जबकि दूसरा फूल लग
okay? I think there was some disturbance. Okay, so so these are all the basic techniques, basic feature extraction techniques. Okay, now So if you, I mean, you would have already done this, but still, I want to give a basic introduction here. So machine learning, what we are doing is we are taking an input, we are doing a feature extraction, classification, everything into to identify the output. Whereas in deep learning techniques, what we do is we combine the feature extraction and classification. What we do is we don't only combine feature extraction and classification, we also do denoising, we also do feature extraction, classification, everything within this particular model itself. Okay, so that is the integration. That is a unique advantage of deep learning, wherein you don't have to understand the discriminative features. You don't have to select it. The model itself select the discriminative features. But the to see then what is your role in it? If the model is going to give you the discriminative features, then you need to do some role, right? So what is that role in it? You need to tune the model in such a way that it extracts the discriminative features. So how do you tune the model? How do you extract discriminative features? That is in your hand. Okay, so now, based on these classifications, you have different kinds of classifiers that can be trained. So we have support vector, machine, discriminant. So this is not only used here in classification as a machine learning model, we also use the final layer of the deep learning model. We have a final layer of feed-forward neural network, right? Okay, I'll just go into it. We will. So this is one of the example that I wanted to show you is a CNN-based network. So you had seen the implementation in the last lecture, but I still want to give you a small introduction to it. We will see the application case study tomorrow. So here you can see I have taken a retinal image, okay, and I have passed it to a CNN network. So what is a CNN network? It has multiple convolution and max pooling layers. What is this convolution layer? I had already told you. It has a kernel. Okay, it has different kernels, different filters, and these filters are being used to extract the information from the image. Okay, and how these information are extracted, these informations whatever being extracted are called to be as features. Okay, they can be modeled as high level features, low level features, and mid level features. What are these features? Basically edges, textures, the shapes, all those things are features that are being extracted. And how are they being extracted? They are extracted by using these predefined filters. Okay, these predefined filters are there in every convolution layer. So you can alter the layer, the number of layers in the convolution. You can, right? So you can alter the number of layers in the convolution, do whatever differences you want in the layers, so that you can extract meaningful information. I'm again and again emphasizing on this because I have seen many students doing one common mistake, that they download a pre-trained network, whatever it is. It's not only convolution CNN network. They download any pre-trained network that is already available. They just press a run button without even understanding what is happening inside that. So you please understand what is happening. You please identify what filters are being used, why they are being used. So whether it will be adaptive for your kind of image, how do you make it adaptive for your image, how many filters you need actually, how many layers you need actually, because depending on this image size, you have to reduce the number of layers. If you had used the same pre-trained network with the image size that is in your hand, what may happen is it may go towards zeros. Okay, so why that happens, why it goes towards zeros, because of something called to be as vanishing gradient that has this problem. But it is actually solved using ResNet and other things. Advancements are there, but still you need to understand the what are the basics of the model, so that you can better implement these things in to extract, to understand the discriminative features that can be used in classification. Now, after the model, this is the model that is being developed. After that, you always have a fully connected feed-forward network. Okay, so this you can replace. You can use any of these models. You can use any of these classification models. You can use a SVM model. You can use naive-Bayes, anything. Here they have used a feed-forward ANN model. It's just nothing but ANN model. You can use MLP here. You can use anything that can use as a class, that can act as a classifier. That's it. Okay. So CNN, if you can think about it, whatever I had told you for the last 1 hour, it is actually put together in one model. That's it. So in one model, I have I have denoising. I can implement segmentation also. Okay, not here, not right now. I can implement segmentation also here. Okay, so if I implement segmentation also using a deep learning model, it will become an ensemble model. That's it. Nothing more. So I can have. Sorry, I already have denoising. I already have feature extraction from this model. So I also have a classification. So whatever we had spoken till now, okay, that is all put together in this model. So if you understand the basics, you will surely understand the deep learning part. Okay, so this we will see in the we will actually start with this in the next class, next lecture. And also one simple case study I will show you. So effect of how we have used a deep learning model to understand the problem of retinal images. Sorry, this is what fundus images. Okay, on due to diabetes. So how the variations in the eyes are happening due to the diabetes condition. So diabetic retinopathy, and you can see there are different problems that can happen in the eye that can be imaged using fundus images, and so we can use different kinds of models to predict what kind of outcome that we are getting. So this is one of the case that we have done. So we segmented the optic cup. This is using a deep learning model. I'm just giving you a case study here. I will explain in detail what we have done. So you can see the optic cup, and also the optic disc cup. There are two parts of this is the center part. You can see this consists of optic cup and optic disc. So you can segment both the things using deep learning models or image processing models. It is not that deep learning models can only be used. That I can emphasize again and again. Okay, and we have already also used these kind of models to segment the blood vessels. Okay, so and we try to understand the connectivity of these blood vessels to see what kind of effects they are having on different case scenarios. And this is one example of image segmentation and how your model is actually trained and evaluated. So we generally use two things. One is dice coefficient and IOU. Okay, so these are all for segmentation models. So when you go for segmentation model, we use the dice coefficient, that is the similarity between the mask and the segmented object, and also the IOU. So these two gives you the similarity metrics and the loss function. Okay, so this is mainly for segmentation. I'm not talking about classification yet. Classification, we use accuracy and other metrics, F1 score, whatever you want to use, you can use. But generally in deep learning models, when you're using for segmentation, you use test coefficient IOU as a metric to train and evaluate the model. Okay, so these are all the these are the for different epochs. We have just plotted it and shown you. But I will talk more about this in the next lecture. Tomorrow we have another lecture, so I will talk more about this and how basically I will start with the case study in neurodegenerative disorders, 3D analysis and other things that we have done. And we will go forward in understanding the aspects of how models can be used to predict and segment the images. Okay, so thank you very much. You can ask if you have any questions regarding the session.
Yes, participants having any question? Yes, any question from participant side?
Okay.
Ma'am, there are one question, ma'am, from my side.
Okay.
That there are different disease detection in case
Yeah.
of medical image processing. So how
Mhm.
can we apply it? How can we add our novelty to detect the detection, early detection, or how we add a
So
novelty in our method so that
okay.
yeah.
See, when we are looking at any any kind of image processing pipelines or image analysis pipeline, the novelty lies in multiple aspects. Okay, it is not only always we are looking only at the accuracy point, or you have to improve the state of the art. It is not always possible to increase the state of the art. That is fine. State of the art is fine, but when we look at early detection and other things, right? So we generally go with the literature. You start from the literature, you try to identify a different aspect of the process. That is, for example, a simple example, if I can give you is, doctors always use retinal imaging, right? So in retinal imaging or in fundus imaging, I will not say retinal image, fundus imaging, they always look at the shape of the what is it, the lens and other things, what the cornea, the shape of the iris, and the shape of the pupil that is present in the eyes. But we can also have another aspect to it, that the texture information, which is already not available. So somebody somewhere would have told that this disease alters um the texture of the ice. Okay, so we can take those information and we can work on it. That will create novelty in. So this is one aspect. Okay, whatever I'm talking about is in one aspect. This is novelty in disease identification case. There is also another case where novelty in methodology. So how can you improve the methodology so that the state of the art is improved? That is the second case. So till now, nobody has achieved 100%, because if you achieve 100%, then there is nothing to work on, right? So it is like we have taken a small sample of always whatever we are working on, a small sample of information. We are not using any population. Yes. So always whatever we are using is not population information. We are using a very small limited number of samples to test our or to validate our model. So it may not always be applicable to other case scenarios, right? So all those things are important. So that is also where novelty can play and novelty can be shown. So there are multiple, if you can see the pipeline, you can divide it into multiple areas where you can show the novelty. So you can focus on one area and develop on that. So it is not that everything should be covered in that particular research. So focus on either you want to improve, you want to target on a different space to improve the disease detection, to improve early diagnosis, or you want to target a different methodology as such, like you want to propose a new segmentation technique so that or you want to improve on the existing segmentation techniques so that you can achieve better accuracy, achieve better state of the art method. So or you can also propose a new novel pipeline itself, complete pipeline itself, that can also give you a good novelty. So it depends on where we want to put in or work in. Yeah.
But ma'am, in case of deep learning methodology,
Yeah.
it extract different type of information, and how we add our different segmentation methods if we want to segment the image or something like
Yeah, you
this.
can. So even in deep learning, we have multiple models for segmentation, right? So we have unit plus plus and other things. They're all custom tailored models, correct? So for example, unit has a particular structure and it has particular number of layers and everything is fixed. So what we can try to do is we can try to alter, or we can try to specifically customize these, like for example, we can think about a particular card that is being made. So if you have a card, a greeting card, you always have a sample card that is there, right? So what we add into it so that it becomes a card for somebody. So that means that you add in touch in some information. So that information is specific to your image, meaning whatever unit plus plus that we are using right now is generally made for natural images. That's what I had told you in the beginning. So everything is made for natural images. Now, right now you can see just last year, I think medical SAM is introduced. SAM is segment anything model. Okay. So this segment anything model was first introduced for what is it? Natural images. Okay. So, or I will say object recognition based images. Like for example, an object is there in an image, you need to segment out that object. SAM was introduced for that. But that same SAM cannot work for medical images because of the nature of the information. The information that is available is almost as similar in through the image, right? So for that, they have already introduced something called as medical SAM, which is a variant of this SAM that was customly made for medical images. So like this, you can introduce some kind of variation in the model itself. Like you can change the hyperparameters, the number of layers, customize it so that for your images, you can show that this is a customized network that can work well for retinal based images or MRI based images. Like that, you can put variations in the model itself so that you will be able to show differences for between the natural images and the medical images. This is one area that is actually still in research, that is still in practice. So no one, we cannot say that this same model will work for same model that works for a particular data set will work the same for the other data set also. So that is not available still now.
Yes, ma'am. If GLCM is we are applying on any
Yeah.
image, then I think 11 to 12 features are there which are extracting from a input sample image. But if we want to extract one or two features which as a output, then what we can do in case of deep learning method, because there are number of features are there which are enhanced, but we
Yes,
are
we can alter
going
the
to
kernel
extract
size.
particular
Kernel.
hmm.
No, for that, if you want to extract particular set of features, you need to go in depth in the code. I have told you that there are kernels that are being introduced in the each convolution layer, right? So in those each convolution layers, we will be having certain kernels. So if you can see 100 kernels will be there in the first layer, 200 kernels will be there in the second layer, and so on and so forth. So those kernels we need to vary so that you can extract what information you want. So right now everything is pre-made, everything is already available, predetermined, and it is fitted. If we can vary that kernels, we will be having different set of information that can be extracted from the image. But what I would say is people are still not looking at that level. Okay. It is already being because the problem with that kernel is because you have hundreds of kernels that are being available. So if you alter one or two kernels, so what you're altering, we will not have an idea. Okay, so that is the reason why everything is predetermined and it is kept. But still, it is a possibility that can be done. And also, one more thing that is possible is you can introduce if you want to use only GLCM matrix, right? So as you had told, you have an image, you want to use GLCM and you want to use a deep learning model. If that is the case, then what I would suggest is you extract the features, GLCM features from the image using a basic image processing technique and use these feature maps as another image. Okay, you take these feature maps as another image, like for example, it's a GLCM matrix is nothing but it will also be another matrix of the image, correct? So you can use that image as an input to the deep learning model that will actually process these GLCM features and it will give you an output. So this is one aspect. The next aspect is you can actually identify which region is giving you good accuracy or which region within your image is not giving you good accuracy. That depends on the we can I have not covered it here, but we can use grad camps. So it comes under explainable AI. So how explainable AI can play an important role in understanding why your model is working actually, how which part of your GLCM matrix is actually working. So you can integrate these two. So GLCM with GradCam can give you a good information on which is actually working out and which is not working out. So that is that we can try. Yeah.
Okay, can we use the GLCM features as the input of the deep learning model as an
Yeah,
input?
sure. We can, yes. But you have to modify the network. Like you cannot use the same network, same CNN network. We have to modify the network if you are using GLCM features.
Okay, that will increase our data set as
Yes. Possibility is there. Yeah.
yeah. Thank you,
Okay.
ma'am. Yeah, is there any other question from participant side? Okay, ma'am. Thank you, ma'am, for such an
There is
informative
one
lecture.
question.
Yeah,
There
yeah,
is one
yeah,
question in the chat window.
yeah. Please.
Yes.
Uh,
Yes, please go ahead, please.
yes.
In coming
Uh,
lectures, is it possible to you to explain the working of hybrid pre-trained model?
yes, yes.
It's there in the
I
chat window.
Tomorrow's lecture. In tomorrow's lecture,
Okay, I will
participant
try
asked
to fit
that.
it.
Yeah, is it possible to explain working of hybrid pertain model?
Pre-trained.
Participant want to participants suggest that if you are delivering in tomorrow's lecture on this topic, so it will give benefited, I think.
Hybrid pre-trained. What kind of hybrid pre-trained network? See, there are different kinds of pre-trained network. Like I don't know. I was just there in the last session.
I think
So last session, sir had
Prachiti Pimple, if you unmute yourself and tell what type of model you want. Prachiti, Prachi. Uh, Participant, unmute
Hello.
yourself. Prach, yes.
Hello, ma'am.
hello.
Actually, I was working. I was working on one of the project where I was trying to combine the different pre-trained models like
Okay.
CNN combination of CNN with the resonate and
Okay.
the
Okay. Okay.
resonate likewise.
Ensemble
So,
models.
ensemble models.
Okay. Uh-huh.
So how exactly if we group all these models and we form a one single model, then how exactly this will work with the sequential manner or in a parallel manner? So I'm confused in that particular
Okay.
concept.
So I will just give you a brief overview right now what it is. Maybe you can contact me. I can give you a good amount of information if you want, because I don't know. I can possibly include in tomorrow's lecture, but we will see about it. But anyway, I will just give you a brief overview. So right now we are combining two models, right? So for example, if you have a CNN model, I had showed you the CNN model, right? Just a minute. I will just share my screen once again.
Yes, yes, ma'am. There is no problem.
Yeah. So if you can, sorry, if you can see this, okay, this is the let go. Actually, I do take a very in-depth class of CNN. I did not cover anything, any aspect because I thought it was already covered. So I generally go into depth with how convolution is happening, how max pooling is happening, and other things. If you want, I can see how to. I'll just cover it in tomorrow's class starting maybe. But still, if you can see here, these layers are actually giving you the feature information. Okay, so convolution, max pooling, convolution, max pooling. What is this convolution means? It is actually extracting some features. Okay, so what features? Edges, textures, structure, structural information, and all those things. So you can think about this is filter one, this is filter two. Like this, you will have n filters, like 100 filters you have. So each filter is going to extract some information, some vertical edge, how many vertical edges are there in the image, how many horizontal edges are there in the image. Like that, each filter is going to extract some information. And what this max pooling does is, okay, I'll
No,
show you
actually,
a
these things are
video.
already covered, and
Okay.
I understood all these
Okay,
things.
you understood
But
all
when
these
we,
things.
yes, yes. But
Yeah.
when we form another model by
Mm.
making a use of VGG16 or the resonate
Okay.
and some other any other model. Now, in
Okay.
that
Okay.
case, how exactly it will work?
Okay, so right now, if you see, I am convolving max pooling. I am flattening it out, right? So here you will have a 1D feature vector, correct?
Right.
So if you can think about it, it is a 1D feature vector. Again, this 1D feature vector acts as an input. You will generally not go into a feed-forward neural network. Rather, here you will stop, correct? You will not differentiate. You will not formulate a classifier to classify it into normal and abnormal. Rather,
So,
you'll
flatten
stop
layer,
here.
we will stop there, right?
Yeah, after the flattened layer, you stop here. This
Okay.
1D feature vector will act as an input to the next layer. It's a sequential network.
Okay.
Generally, we use sequential network if in your case.
Hmm.
But we can use hybrid networks also that we have tried. If you can have different kinds of images of the same objects. Like for example, of this object, I have this fundus image. I also have a normal image, normal camera image of the same object. Then I can use another network parallelly. Okay, and the information from this network and the information from this network will be combined. It will be put together, like concatenated, I will say. So, and then it will be taken to the feed forward network or any classifier or anything that will classify it into normal and abnormal, or whatever you want you can do, how many ever classes you want you can have. So it depends on what you want. So you can either go in a sequential way or you can go in a parallel way, depending on the information that is available to you. You can also go in a parallel way in another, like for example, the same image, you can give parallelly to another network that will extract a different set of information. Like for example, BGG16 will extract different set of information that you can put together and give it to a feed forward network. That will increase the feature space, the size of the feature vector actually.
Okay, so for each of this model, when we run parallelly, when we use this parallel approach, so every time each model will work till flatten layer, and after that we combine the result, and that will get passed to the
Exactly.
FCC, that fully connected network, right?
Yes, correct, correct, correct.
Okay. And in a sequential, how we do after flatten layer, we pass on the one-dimensional vector to the another model, and likewise
Yes.
the third model or the fourth model.
Yes,
And then we
but
pass the
you need to be very careful in that because you will encounter with, this is a 1D array, right? So you need to be very careful in that because you may encounter zeroing of the 1D array. So you need to select a model. You cannot use a VGG16 after this. It will degrade your results. So you need to select the model in particular way that it is helpful in extracting the information. It shouldn't degrade the extracted information.
Which is more used, like parallel is better to go with other sequential.
Again,
As
you
per
you
your
have to.
uh,
It depends on the image. It depends on what is there in hand. Like what is the information that is there in hand. It will vary for each image, each type of classify, whether you want to classify it, whether you want to segment it, each type of information it will vary.
Okay.
So if you can tell me what you are working in, then I can probably suggest. Maybe we can have you can contact me, I can help you out.
Ma'am, you can provide your email ID. Or the
Sure, okay. You can note down my email ID. This is my email ID. It's there. So you can contact me. I can help you out in whatever best way I can.
Okay, ma'am. Thank you so much, ma'am.
Madam, can you give a contact number?
Yeah. So you can note down. It's 866.
Okay.
866.
Yes.
722.
722.
03.
03.
64.
64. Okay, madam.
Yeah.
Are you conducting tomorrow hands-on session, madam?
I may not give hands-on because I think already hands-on is given. So I would give you different case studies which we have carried out based on the deep learning models and image processing techniques and other things. So whatever we are doing work, so I will just give you an introduction so that it will be helpful in progressing forward.
Okay, okay. Okay, thank you, ma'am.
Thank you.
Thank you.
Any other question from participant side? Okay, ma'am. Thank you. Thank you for today's informative lecture. And
Thank
we'll
you, sir. Thank you.
join
Thank you for
tomorrow.
inviting me. Thank you for giving the opportunity. Thank you. Yeah, we'll meet tomorrow. Yeah, sure.
Okay. Thank you. Good night.
Thank you, ma'am. And participants are requested to join tomorrow at 2 p.m. Because our session will start tomorrow earlier.